Most people know Einstein discovered that time dilates and space curves, but few grasp the deeper philosophical architecture underlying these discoveries. Einstein wrestled with profound questions. What can we truly know about reality? How do we bridge the gap between our perceptions and the actual world? Is the universe fundamentally rational and comprehensible? Can nature be both deterministic and unpredictable? These questions drove his scientific work, and his answers remain controversial, debated, and influential among physicists, philosophers, and thinkers today. This exploration examines Einstein's complete philosophical framework. We will investigate his theory of knowledge, his beliefs about reality, his views on determinism and probability, his conception of time and simultaneity, his thoughts on religion and God, his political philosophy, and his vision of human nature. We will examine where his ideas succeeded brilliantly, where they failed or faced serious challenges, and how scholars continue to debate his legacy. This is not hero worship. Einstein made profound errors and held positions that contemporary evidence has challenged. Understanding both his insights and his mistakes reveals the full depth of his intellectual achievement. Part 1. The foundation of Einstein's epistemology. How we know what we know. Einstein built his entire intellectual edifice on a revolutionary theory of knowledge. Understanding this foundation is essential because it explains why he made the scientific choices he did, and why he rejected certain conclusions that seemed obvious to his contemporaries. At the heart of Einstein's epistemology, which means his theory of how humans acquire knowledge, lies a profound skepticism about direct perception. Since childhood, Einstein questioned whether our senses give us reliable access to reality. He recognized that what we perceive as solid matter is mostly empty space. What we experience as continuous motion is actually discrete molecular collisions. What seems simultaneous to one observer occurs at different times to another moving observer. This realization shaped everything that followed. Einstein called himself a convinced realist, meaning he believed an objective reality exists independent of human observation. This seems obvious, but it became deeply controversial in quantum mechanics. For Einstein, the universe existed with definite properties, whether or not anyone looked at it. A tree falling in a forest makes sound waves regardless of observers. The moon exists even when nobody watches it, as he famously argued against the quantum physicist Niels Bohr. However, Einstein's realism came with a critical caveat that separated him from naive realism. He argued that we never directly perceive reality itself. Instead, we construct mental models, what he called free creations of the human mind, that we then test against observations. Think of it this way. Imagine you are in a locked room with several small windows. Through these windows, you catch glimpses of movement outside. You might theorize that a parade is passing by. You refine your theory by checking whether new glimpses confirm your expectations. But you never step outside to verify directly. Your theory might be excellent, extraordinarily useful, yet never completely certain. This analogy captures Einstein's view of all scientific knowledge. Our theories are sophisticated constructs, not simple copies of reality. Mathematics does not exist out there in nature waiting to be discovered like gold in a mountain. Instead, humans invented mathematical systems as tools for organizing our experience. The shocking thing, which Einstein called a miracle, is that these inventions work so remarkably well at predicting natural phenomena. This led Einstein to a position called critical rationalism mixed with empiricism. Rationalism means using reason and logic to understand the world. Empiricism means using sensory experience and observation. Einstein combined both but made reason primary. He believed that truly revolutionary theories come from creative intuition and logical thinking, not from simply accumulating observations. Facts alone never tell you what theory to build. You need imaginative leaps, thought experiments, and logical deduction. Consider how Einstein discovered special relativity in 1905. He did not perform new experiments or gather new data. Instead, he imagined chasing a light beam at light speed when he was 16 years old. He asked, "What would I see?" This thought experiment revealed a contradiction between existing physics theories. Solving that contradiction through pure reasoning led to revolutionary conclusions about time and space. Only afterward did he and others devise experiments to test his predictions. This approach had profound implications. Einstein argued that scientific theories are radically underdetermined by evidence. This technical term means that the same observational data can support multiple, incompatible theories. Imagine detective work. The same clues might fit several different narratives about who committed a crime. Similarly, the same experimental results might fit different theories about how nature works. Therefore, choosing between theories requires more than just checking observations. It requires judgment about simplicity, elegance, logical consistency, and explanatory power. Einstein explicitly valued certain theoretical virtues. First, simplicity. Theories should be as simple as possible, but no simpler, as he allegedly said. Second, unification. Theories should explain diverse phenomena through common principles. Third, logical consistency. Theories must not contradict themselves. Fourth, what he called inner perfection. Theories should feel complete and natural, not contrived. Fifth, explanatory depth. Theories should answer why questions, not merely describe what happens. These values explain many of Einstein's most famous disagreements. When quantum mechanics appeared to describe nature using inherent randomness and observer-dependent reality, Einstein rejected it. Not because it made wrong predictions, quantum mechanics worked brilliantly. He rejected it because it violated his theoretical values. A truly fundamental theory, Einstein insisted, should be deterministic, meaning effects follow necessarily from causes. It should be realistic, meaning it describes an observer-independent reality. And it should be local, meaning influences cannot travel faster than light. This reveals something crucial about Einstein's method. He did not simply follow evidence wherever it led. Instead, he used philosophical principles to judge which theories could possibly be true, even if they explained current observations. He believed that nature, at its deepest level, must be comprehensible to human reason. If a theory seemed to violate rationality or introduce mysterious, unexplainable elements, Einstein suspected it was merely a transitional approximation, not the final truth. This philosophical stance had both strengths and weaknesses. The strength, it enabled revolutionary breakthroughs. By trusting reason over accumulated observations, Einstein overthrew Newton's physics, which had seemingly unlimited empirical support. He saw deeper principles that observations alone could not reveal. The weakness. It sometimes made Einstein dismissive of genuine discoveries. Quantum mechanics has withstood nearly a century of experimental testing. Einstein's philosophical objections, however reasonable, turned out to reflect his preferences rather than nature's actual structure. Scholars continued debating whether Einstein's epistemology remains defensible. Some philosophers argue that his emphasis on theoretical virtues, like simplicity and unification, reflects aesthetic prejudices rather than reliable guides to truth. Why should the universe be simple? Why should human mathematical intuitions match cosmic structure? These questions remain open. Other thinkers defend Einstein's approach, arguing that theoretical virtues have proven remarkably successful historically. Scientific progress often requires leaps beyond available evidence. The contemporary relevance appears in modern physics' search for a unified theory of everything. Physicists pursuing string theory or loop quantum gravity often defend their approaches using Einstein-style arguments: elegance, unification, mathematical beauty. Critics respond that without experimental evidence, these virtues might lead us astray. This debate essentially continues Einstein's foundational questions about how we know what we know and what standards we should use to judge competing theories about reality. Part 2. Relativity's Philosophical Revolution. Time, Space, and Simultaneity. Einstein's theories of relativity destroyed assumptions humanity held for thousands of years. Before 1905, everyone believed time flowed uniformly everywhere. A minute on Earth equaled a minute on Jupiter, a minute anywhere in the cosmos. Space formed a fixed, unchanging stage where events occurred. These assumptions seemed self-evident. Einstein proved them completely wrong. The philosophical earthquake began with a deceptively simple question. What does it mean for two events to happen simultaneously? Imagine a train moving past a platform. Lightning strikes both ends of the train at what seems like the same instant to someone standing on the platform. But a passenger sitting at the train's centre, moving toward one lightning strike and away from the other, sees the forward strike first. The light from the forward strike reaches them sooner because the train moves toward it. Which observer is correct? Pre-Einstein physics answered, calculate away the light travel time, and you will find the real simultaneous moment. But Einstein asked a more radical question. What would you use to calculate? You need to know how fast light travels. How do you measure light speed? You need synchronized clocks at different locations. How do you synchronize distant clocks? You need to know if events are simultaneous. You have gone in a circle. There is no way to break out and discover absolute simultaneity. Einstein concluded that simultaneity is not absolute but relative to the observer's state of motion. Events simultaneous for one observer occur at different times for another observer moving relative to the first. This is not an illusion or perceptual mistake. There exists no privileged perspective that reveals the true order. Both observers are equally correct within their reference frames, which means their perspective from their state of motion. This conclusion demolishes common-sense notions of time. We instinctively imagine a universal now slicing through the cosmos, a present moment existing everywhere simultaneously. Einstein showed this picture is fundamentally wrong. There is no cosmic now. Different observers carve the universe into past, present and future in different, equally valid ways. Your present moment on Earth has no objective correlation with any particular moment on a distant star. The philosophical implications stagger the imagination. Consider causality, the relationship between cause and effect. We assume causes always precede effects. I press a button, then the light turns on. The button press causes the illumination. But if simultaneity is relative, could different observers disagree about which event happened first? Could one observer see the light turn on before I press the button? Einstein's answer provides relief. No, this cannot happen for events that could causally influence each other. Special relativity preserves causal order for connected events. If event A can cause event B, all observers agree A precedes B. However, for events too far apart to influence each other, meaning events separated by distances greater than light could travel in the available time, observers can disagree about temporal order. These causally disconnected events have no objective temporal relationship. This leads to deeper strangeness. Time itself becomes a dimension similar to space, not fundamentally different. In Newtonian physics, time marches forward universally while objects move through three-dimensional space. In relativity, we inhabit four-dimensional space-time. Moving through space means rotating your trajectory through space-time, exchanging some time direction for space direction. Here is a concrete example of what this means. Imagine two twins, Alice and Bob. Alice boards a spacecraft and travels at 90% of light speed to a distant star and returns. Bob remains on Earth. When Alice returns, she has aged perhaps 5 years. Bob has aged 50 years. This is the famous twin paradox, though it is not actually paradoxical. Alice's high-speed journey through space meant she travelled more through space and less through time in space-time. She literally experienced less time. This is not science fiction or theoretical speculation. Physicists have verified time dilation countless times. Atomic clocks flown on airplanes run slower than identical clocks left on the ground by precisely the amount relativity predicts. Particles called muons, created in the upper atmosphere, should decay before reaching Earth's surface based on their known lifetime. But travelling at near light speed, time slows for them from our perspective, allowing them to reach the ground before decaying. The implications for human experience are profound. We are all time travellers, moving into the future at different rates depending on our velocity and the gravitational fields we experience. Astronauts on the International Space Station age slightly slower than people on Earth because they move faster and experience weaker gravity. The difference amounts to mere milliseconds over months. But the principle is absolute. Your personal experience of duration depends on your path through space-time. General relativity, which Einstein published in 1915, made the situation even stranger. Einstein unified gravity with geometry. He showed that massive objects curve space-time itself. Planets orbit stars not because of a mysterious force pulling them, but because stars warp space-time, and planets follow the straightest possible paths through this curved geometry. Gravity is geometry. This geometric interpretation revolutionized philosophy of space. For centuries, philosophers debated whether space is substantival, meaning it exists as a real thing, or relational, meaning it is merely the arrangement of objects. Newton believed space was substantival, an absolute framework. Leibniz argued it was relational, just a way of describing how objects are positioned relative to each other. Einstein's answer? Both and neither. Space-time is not simply the arrangement of matter, so pure relationalism fails. Space-time has properties and structure independent of material objects. It can curve, ripple, and carry energy as gravitational waves. Yet space-time is not a Newtonian absolute container independent of matter. Matter and energy determine space-time's shape. Space-time tells matter how to move, and matter tells space-time how to curve, as the physicist John Wheeler memorably summarized. Philosophers call this middle position structural realism. Space-time is real, but its reality consists of geometric relationships rather than independent substance. Think of it as dynamic architecture rather than a static stage. General relativity also enables bizarre possibilities that challenge intuition. Black holes are regions where space-time curves so extremely that nothing, not even light, can escape from inside a boundary called the event horizon. Time behaves extraordinarily near black holes. From an outside observer's perspective, an astronaut falling toward a black hole appears to slow down asymptotically, never quite reaching the horizon. From the astronaut's perspective, they cross the horizon in finite time and plunge toward the singularity at the center, a point where space-time curvature becomes infinite and our equations break down. Which perspective is correct? Both, within their respective reference frames. This is the relativity of temporal experience taken to its extreme. Even more strangely, general relativity permits solutions where time forms closed loops. These are called closed time-like curves, which allow travel backward in time. The physicist Kurt Gödel, Einstein's colleague at Princeton, discovered such solutions. In Gödel's rotating universe, you could board a spaceship, travel a particular trajectory, and arrive back at Earth before you departed. You could shake hands with your younger self. Einstein found this disturbing. It seemed to violate causality and create logical paradoxes. What if you travelled back and prevented your younger self from boarding the spaceship? These paradoxes suggested that Gödel's solutions, while mathematically valid, might not describe physical reality. Perhaps nature has laws preventing closed time-like curves from forming. Physicists call this the chronology protection conjecture. The debate continues today. Some physicists argue quantum mechanics naturally prevents time travel paradoxes through consistency requirements. Others suggest parallel timelines or many worlds interpretations solve the problems. Still, others believe fundamental yet undiscovered physics forbids time travel absolutely. These questions reveal how Einstein's relativity transformed the philosophy of time from an abstract discussion into empirical science. Questions about time's nature now require understanding physics, not just logical analysis. This itself is philosophically significant. It shows that metaphysics, the branch of philosophy studying reality's fundamental nature, cannot proceed independent of science. However, Einstein's revolution faced serious critiques. The philosopher Henri Bergson, his contemporary, argued that Einstein confused mathematical time with lived, experienced time. Bergson distinguished between clock time, which physics measures, and duration, which we experience directly through consciousness. Physics might show that moving clocks tick slower, but this does not capture the qualitative essence of temporal experience, the feeling of time passing. Einstein dismissed Bergson's critique, arguing that experienced time must ultimately reduce to physical time. But Bergson identified a genuine problem. Does physics exhaust reality? Or do conscious experiences have properties that physical descriptions miss? This debate continues in philosophy of mind today. Another critique concerns relativity's determinism. Special and general relativity are deterministic theories. Given complete information about the universe at one time, the equations determine everything that happens at all other times, past and future. This seems to eliminate human free will and moral responsibility. If the future is already determined by past conditions, how can we be responsible for our choices? Einstein acknowledged this tension, but accepted determinism. We will examine his views on free will more deeply in later parts. For now, note that relativity's determinism assumes complete knowledge of initial conditions and perfect ability to solve the equations. In practice, both are impossible. Additionally, general relativity permits singularities where determinism breaks down, and combining relativity with quantum mechanics introduces fundamental unpredictability. A more technical philosophical problem involves defining identity through time. If objects are actually four-dimensional space-time worms extending through time, what makes you at age 10 the same person as you at age 50? Pre-relativistic philosophy could say, you are the same person because you persist through time as a three-dimensional object. But in space-time, you are a four-dimensional structure. Different temporal slices are as distinct as different spatial locations. This undermines traditional notions of personal identity and persistence. Philosophers have proposed various solutions. The perdurance theory says you are a four-dimensional object, and your younger and older selves are merely temporal parts. The endurance theory tries to preserve three-dimensional persistence, despite space-time structure. Neither solution is fully satisfying, and the debate remains active in metaphysics. Perhaps the deepest philosophical impact concerns the nature of scientific explanation. Pre-Einstein physics explained events by identifying forces and causes operating through time. General relativity, instead, explains by showing how events fit into space-time geometry. Rather than asking what force makes planets orbit, we ask what is the geometric structure of space-time near a massive star. This shifts from dynamical explanation, which involves causes producing effects, to structural explanation, which involves geometric relationships. Some philosophers argue this represents genuine explanatory progress. Others worry we have lost something essential. Does showing that gravity is geometry really explain gravity, or does it merely redescribe the phenomenon? When we say massive objects curve space-time, what mechanism produces this curvature? Einstein's equations describe how much curvature results from a given mass-energy distribution. but they do not explain why mass-energy curves space-time in the first place. This leads to the limits of Einstein's relativistic revolution. While relativity transformed our understanding of space, time and gravity, it remains a classical theory that breaks down at quantum scales and at singularities. It cannot explain what happens inside black holes at the singularity. It cannot describe the universe's first moments after the Big Bang. It treats space-time as smooth and continuous, but quantum mechanics suggests space and time might be granular at the smallest scales. Modern physics seeks a quantum theory of gravity that would supersede general relativity, just as general relativity superseded Newtonian gravity. Candidates include string theory, loop quantum gravity, and causal set theory. All face enormous mathematical difficulties and lack experimental evidence. The search continues Einstein's dream of unification, which we will explore further in Part 6. The contemporary relevance of Einstein's relativistic philosophy appears throughout modern physics and philosophy. The discovery of gravitational waves in 2015, exactly 100 years after Einstein predicted them, vindicated his geometric view of gravity. These ripples in space-time fabric, produced by colliding black holes billions of light-years away, confirmed that space-time is a dynamic physical reality. It is not merely mathematical abstraction. Yet quantum mechanics continues to challenge relativity's classical determinism. Quantum entanglement seems to involve instantaneous correlations across space, potentially conflicting with relativity's insistence that no influence travels faster than light. Reconciling quantum mechanics with general relativity remains the greatest challenge in fundamental physics. Einstein's relativistic revolution thus remains incomplete, awaiting unification with the quantum revolution he helped start, but never accepted. Part 3. The Great Quantum Debate: Determinism, Causality and Reality. Einstein's relationship with quantum mechanics embodies one of science's greatest ironies. He pioneered quantum theory in 1905 by explaining how light behaves as discrete packets of energy called quanta, not continuous waves. This work earned his Nobel Prize. Yet Einstein spent the last 3 decades of his life arguing that quantum mechanics, as developed by Niels Bohr, Werner Heisenberg and others, could not be the final truth about nature. His objections were not mathematical, but deeply philosophical. To understand this debate, we must grasp what quantum mechanics says about reality. Classical physics, including Einstein's relativity, assumes the world has definite properties independent of observation. A particle has a specific position and velocity at every moment, whether or not anyone measures it. Measurement reveals pre-existing properties. Quantum mechanics shatters this assumption. According to the Copenhagen interpretation, developed primarily by Bohr and Heisenberg, particles do not have definite properties until measured. Before measurement, a particle exists in a superposition, a combination of multiple possible states simultaneously. The particle is not secretly in one definite state that we simply do not know. It genuinely exists in multiple states at once. Measurement forces the particle to collapse into one definite state. Which state appears is fundamentally random, governed only by probabilities that the theory calculates precisely. But nothing determines which particular outcome occurs in any individual measurement. God plays dice in quantum mechanics view. Einstein found this philosophically unacceptable. His objections crystallized in a famous 1935 paper written with Boris Podolsky and Nathan Rosen, known as the EPR paper after their initials. The paper presented a thought experiment, later refined by physicist David Bohm, that Einstein believed exposed quantum mechanics' incompleteness. Imagine two particles interact and then separate, flying off in opposite directions. Quantum mechanics describes them as entangled, meaning their properties remain correlated even across vast distances. Measuring one particle's spin, which is a quantum property similar to rotation, instantly determines the other particle's spin, even if the particles are light-years apart. If you measure the first particle and find its spin pointing up, the second particle's spin must point down. The Copenhagen interpretation says the first particle had no definite spin before measurement. It existed in a superposition of up and down simultaneously. Measurement collapsed it to one state. Somehow this instantaneously affected the distant second particle, collapsing it to the opposite state. This seems to violate relativity's prohibition against faster-than-light influences. Einstein argued that a more reasonable explanation exists. Perhaps both particles had definite spins from the moment they separated. Measuring the first particle simply reveals information that was already determined. No mysterious, instantaneous influence crosses space. The correlations arise from common past causes, not spooky action at a distance, as Einstein mockingly called quantum entanglement. This view requires hidden variables, additional properties beyond what quantum mechanics describes, which determine measurement outcomes. Quantum mechanics gives only probabilities because it is incomplete, lacking these hidden variables. A future, more complete theory would be deterministic, Einstein believed, restoring certainty and eliminating randomness. The EPR argument seemed powerful. But in 1964, physicist John Bell proved a remarkable theorem that transformed the debate. Bell showed that any theory using local hidden variables, meaning hidden properties that do not involve faster-than-light influences, must satisfy certain mathematical inequalities. Quantum mechanics violates these Bell inequalities. This meant the question could be settled experimentally. Perform the right measurements on entangled particles, and see whether the results satisfy Bell's inequalities or violate them as quantum mechanics predicts. Starting in the 1970s, physicists performed increasingly sophisticated tests. The results consistently violated Bell's inequalities, supporting quantum mechanics. These experiments won the 2022 Nobel Prize and have profound philosophical implications. They prove that Einstein's preferred picture, with particles having definite properties determined by local hidden variables, cannot be correct. Nature genuinely exhibits non-local correlations. Measuring one particle instantaneously affects its distant entangled partner. However, this does not vindicate the Copenhagen interpretation entirely. Bell's theorem shows that any theory matching quantum mechanics predictions must be either non-local, involving faster-than-light correlations, or non-realistic, meaning particles lack definite properties before measurement, or both. Physicists and philosophers disagree about which horn of this dilemma to accept. Some interpretations preserve determinism by accepting non-locality. Bohm developed a hidden variable theory where particles have definite positions at all times, guided by a quantum pilot wave that propagates instantaneously across space. Bohm's theory reproduces all quantum predictions while maintaining Einstein's realism and determinism. But it pays the price of non-locality, violating Einstein's other core principle that no influences travel faster than light. Other interpretations embrace indeterminism while preserving locality. The many worlds interpretation, proposed by Hugh Everett in 1957, says the wave function never collapses. Instead, every measurement splits reality into multiple parallel universes, each realizing one possible outcome. In one universe, you measure spin up. In another universe, an identical copy of you measures spin down. Both outcomes occur, just in different branches of reality. This interpretation strikes many people as wildly extravagant, multiplying universes to avoid randomness. But it takes quantum mechanics mathematics completely seriously, without adding collapse postulates or hidden variables. Physicist David Deutsch argues it is the simplest interpretation, despite seeming complex, because it requires fewer assumptions. A third approach, called cubism, treats quantum mechanics as describing our knowledge or beliefs about measurement outcomes rather than describing reality itself. From this perspective, the wave function represents subjective information, and collapse reflects updating our knowledge, not a physical process. Different observers can assign different wave functions to the same system based on their different information. Einstein would have rejected all these interpretations. Bohm's theory, while deterministic, uses non-locality that Einstein found unacceptable. Many worlds multiplies realities unnecessarily and is unfalsifiable. Cubism denies objective reality by making quantum mechanics subjective. None satisfies Einstein's core principles: realism, locality, determinism, and objectivity. The deeper philosophical issue concerns what scientific theories should explain. Einstein believed fundamental theories should describe reality as it is, independent of observers and measurements. Quantum mechanics, in most interpretations, refers essentially to measurements and observers. The theory tells us what happens when we measure, but says little about what exists when nobody looks. Einstein found this instrumentalist approach, which treats theories as mere prediction tools without describing reality, philosophically impoverished. He insisted physics should be about nature itself, not just human interactions with nature. As he famously asked Bohr during their debates, "Do you really believe the moon exists only when you look at it?" Bohr responded that the question misunderstands quantum mechanics. We cannot meaningfully discuss reality independent of measurement because measurement and measured system form an inseparable whole. Classical concepts like position and momentum, which we use to describe nature, only make sense within specific experimental contexts. Asking about reality in itself, apart from any possible measurement, asks a meaningless question, according to Bohr. This complementarity principle, Bohr's philosophical framework, says that complete description requires multiple, seemingly contradictory perspectives. Light behaves as waves in some experiments, as particles in others. These are not opposing properties of light itself, but complementary ways humans can investigate light using different experimental arrangements. Which aspect manifests depends on our measurement choice. Einstein never accepted this. He believed Bohr was abandoning the goal of objective knowledge and replacing it with pragmatic description of human experience. Physics was becoming phenomenology, the study of appearances rather than ontology, the study of what exists. Einstein saw this as intellectual defeat, accepting limitations on human knowledge rather than pushing toward deeper understanding. Modern philosophers of physics remain divided. Some argue that Einstein's realist principles are outdated metaphysical prejudices. Science should describe observable phenomena and make accurate predictions. Whether unobservable reality really exists with definite properties is a pseudo-question beyond science's scope. This view, called scientific anti-realism, has respectable pedigree dating to philosophers like Ernst Mach, who influenced young Einstein before Einstein later rejected this position. Others defend Einstein's realism. They argue that science's success depends on approximately true descriptions of unobservable reality. Atoms, electrons, quarks, and quantum fields are not mere calculational devices. They are real entities whose properties cause observable phenomena. A theory that refuses to describe reality beyond observations abandons explanatory depth for predictive accuracy alone. The debate extends to quantum mechanics' practical applications. Quantum computers harness superposition to perform calculations impossible for classical computers. Quantum cryptography uses entanglement to guarantee secure communication. These technologies work spectacularly, regardless of interpretational disputes. Does this prove that questioning quantum mechanics' foundations is pointless philosophy? Einstein would say no. Practical success does not prove theoretical completeness. Newtonian mechanics worked brilliantly for centuries before relativity revealed its limitations. Similarly, quantum mechanics might be a highly accurate approximation to some deeper theory that restores determinism and realism. Without pursuing foundational questions, we might never discover that deeper theory. Indeed, recent experimental advances are revealing new puzzles. Quantum gravity research suggests that space-time itself might be emergent from more fundamental quantum information structures. Black hole physics reveals deep connections between quantum mechanics, thermodynamics, and gravity that nobody fully understands. These frontiers might ultimately require the kind of complete theory Einstein sought. One contemporary debate concerns the measurement problem, which quantum mechanics has never fully solved. Why and how does the wave function collapse during measurement? The theory says collapse happens but does not explain it. Various interpretations offer different answers, from many worlds' denial that collapse occurs to spontaneous collapse theories that add new physics to quantum mechanics. Einstein identified this problem early, calling measurement's special role in the theory artificial and unsatisfying. Another unresolved issue concerns quantum mechanics' relationship with time. Standard quantum mechanics treats time as an external parameter, not a quantum observable like position or momentum. This creates tensions with general relativity, where time is part of space-time geometry and observers moving at different velocities experience time differently. Combining quantum mechanics with relativistic time remains an open problem that might require reconceptualizing both theories. Einstein's critique also highlighted quantum mechanics' indeterminism as a fundamental flaw. Modern philosophers distinguish between ontological and epistemic indeterminism. Ontological indeterminism means the future is genuinely open, not determined by the present. Epistemic indeterminism means we cannot predict the future because of knowledge limitations. Classical chaos theory exhibits epistemic indeterminism, systems so sensitive to initial conditions that tiny uncertainties explode into complete unpredictability, but remain ontologically deterministic. Quantum mechanics seems to involve ontological indeterminism. Measurement outcomes are not simply unknown, they are fundamentally indeterminate until measurement occurs. Einstein believed this threatened causality and rationality. If events occur without sufficient causes, how can we understand nature through reason? Defenders of quantum indeterminism respond that Einstein confused determinism with comprehensibility. Nature can be rationally understandable and mathematically describable while remaining indeterministic. Quantum mechanics provides perfect probabilistic predictions. Perhaps this represents the deepest level of understanding nature permits. This raises the question, what makes an explanation satisfying? Einstein wanted deterministic explanations that showed necessity. Given these causes, these effects must follow. Quantum mechanics offers probabilistic explanations. Given these conditions, these outcomes occur with these probabilities. Is probabilistic explanation genuinely explanatory or merely descriptive? Philosophers remain divided. Some argue that probabilistic causation is perfectly legitimate. Many everyday explanations use probabilities. Smoking causes cancer probabilistically, not deterministically. Others maintain that probabilistic explanations are incomplete and should ultimately reduce to deterministic mechanisms, even if unknown. Einstein's position also reflected his scientific practice. His greatest discoveries came from seeking unified, deterministic explanations. This methodology succeeded brilliantly for relativity. But quantum mechanics seemed to require abandoning this approach. Perhaps Einstein's methodology, while extraordinarily fruitful in some domains, was unsuited to quantum phenomena. The stakes extend beyond physics. If quantum indeterminism is fundamental, it might provide room for free will in an otherwise deterministic universe. Some philosophers and neuroscientists argue that quantum randomness in brain processes could enable genuine choices not determined by prior causes. Others respond that random quantum events hardly constitute meaningful free will, which seems to require control and rationality, not mere indeterminism. Einstein himself did not believe indeterminism rescued free will. He was a compatibilist about free will, holding that freedom and determinism are compatible. We will explore this in Part 8. But his rejection of quantum indeterminism did not stem from worries about free will. It stemmed from his conviction that fundamental physics should describe a rational, comprehensible reality. The quantum debate also reveals tensions between mathematical beauty and empirical adequacy. Quantum mechanics' mathematical structure is extraordinarily elegant. Its predictions have been verified to staggering precision. Yet its conceptual foundations remain murky and disputed nearly a century after its development. Should we accept this situation, or demand both mathematical elegance and conceptual clarity, as Einstein insisted? Contemporary physics faces similar tensions in string theory and quantum gravity research. These theories exhibit beautiful mathematics, but lack experimental evidence. Critics argue they repeat quantum mechanics' mistake, prioritizing mathematical formalism over clear physical interpretation. Defenders respond that Einstein himself used mathematical beauty to discover relativity before experiments confirmed it. Einstein's quantum legacy thus remains ambiguous. He was wrong about hidden variables, wrong about quantum mechanics being incomplete in the way he thought, wrong about determinism being restorable without abandoning locality. But he was right that quantum mechanics raises deep conceptual problems. He was right that physics should aspire to objective description of reality. He was right that foundational questions matter, not just practical applications. Perhaps most importantly, Einstein demonstrated how philosophical principles can guide scientific investigation. His objections to quantum mechanics were not obscurantist resistance to new ideas. They were principled arguments based on carefully articulated criteria for acceptable theories. Even when wrong, his arguments clarified what was at stake and pushed the field toward deeper understanding. The experimental tests of Bell's theorem would never have happened without Einstein's EPR thought experiment provoking them. The quantum debate continues to evolve. New interpretations emerge regularly. Experimental techniques allow testing scenarios that were once pure philosophy. Quantum information theory has transformed how physicists think about quantum mechanics, emphasizing information and correlations over particles and waves. These developments might eventually lead to the conceptual clarity Einstein sought, or they might show that quantum weirdness is simply how nature is at the fundamental level. Part 4. Einstein's God, Religion, Spinoza, and Cosmic Religion. Einstein's religious views were complex, subtle, and widely misunderstood during his lifetime and after. He rejected traditional religious belief in a personal God who answers prayers, rewards virtue, or intervenes in natural processes. Yet he spoke frequently about God, causing confusion among both believers who claimed him and atheists who dismissed him. Understanding Einstein's conception of God requires examining his intellectual relationship with the 17th century philosopher Baruch Spinoza. Spinoza, a Jewish-Dutch philosopher, developed a radical reinterpretation of God. Traditional theology distinguishes God from nature. God is a supernatural being who created the universe and can miraculously intervene in natural law. Spinoza collapsed this distinction entirely. For him, God and nature are identical. There is no supernatural realm separate from the natural world. Spinoza's God is not a conscious person with desires, emotions, or purposes. Rather, God is the totality of nature itself, operating according to eternal, rational laws. Everything that exists is part of God, and everything follows necessarily from God's nature, just as mathematical theorems follow necessarily from axioms. Free will, miracles, and divine punishment are illusions arising from our incomplete understanding. This pantheistic view, equating God with nature, was condemned as atheism in Spinoza's time. Spinoza was excommunicated from the Jewish community, and his works were banned by Catholic and Protestant authorities. But his philosophy profoundly influenced the Enlightenment and later thinkers, including Einstein. Einstein discovered Spinoza's writings as a young man and found in them a philosophical worldview that matched his scientific intuitions. he repeatedly declared himself religious in Spinoza's sense. When asked if he believed in God, Einstein responded, "I believe in Spinoza's God, who reveals himself in the lawful harmony of all that exists, not in a God who concerns himself with the fate and actions of human beings." This Spinozistic religion manifests as Einstein's cosmic religious feeling, which he described as the most profound emotion we can experience. It is the knowledge that something impenetrable, both beautiful and terrible, exists beyond our limited understanding. Contemplating the universe's rational structure, its mathematical elegance, and its comprehensibility to human reason fills Einstein with awe and reverence. This emotional response to cosmic order constituted his religiosity. For Einstein, scientific investigation was religious worship. Discovering nature's laws meant revealing God's structure. The fact that the universe follows comprehensible mathematical principles seemed miraculous. Why should human reason, which evolved for survival on African savannas, be capable of understanding quantum mechanics or general relativity? Einstein called this the eternal mystery, the comprehensibility of the universe. This comprehensibility suggested to Einstein that the universe embodies rationality at its core. Nature is not arbitrary or chaotic. It follows elegant mathematical laws that human minds can discover through reason. This cosmic rationality was Einstein's God. Unlike traditional theology's personal deity, Einstein's God does not love, judge, or intervene. It simply exists as the rational structure of reality. Einstein explicitly rejected anthropomorphic conceptions of God. He found the idea of a God who rewards and punishes, feels jealousy or wrath, or cares about human behavior childish and primitive. Such beliefs project human qualities onto the cosmos. They arise from fear and desire for comfort, not from genuine understanding. This put Einstein at odds with organized religion. Traditional Judaism, Christianity, and Islam all posit a personal God who relates to humanity, hears prayers, and expects moral behavior. Einstein considered these conceptions primitive superstitions, though he expressed this view more diplomatically in public. He wrote privately, "The word God is for me nothing but the expression and product of human weaknesses. The Bible a collection of venerable but still rather primitive legends." Yet Einstein did not consider himself an atheist. He distinguished between rejecting anthropomorphic religion and rejecting cosmic religiosity altogether. Atheism, in his view, focused too much on what one does not believe, rather than on the positive emotional and intellectual response to the universe's structure. Einstein described his position as agnosticism, tempered with Spinozistic pantheism. His religious views caused constant public controversy. Religious leaders criticized him for denying God's personality and providence. Atheists criticized him for using religious language at all. During a 1929 interview, when asked if he believed in God, Einstein replied, "I believe in Spinoza's God." This statement was widely misunderstood as endorsing traditional theism. Einstein received numerous letters from religious believers asking him to clarify his views. To one correspondent he wrote, "I do not believe in a personal God, and I have never denied this, but have expressed it clearly." He continued, "If something is in me which can be called religious, then it is the unbounded admiration for the structure of the world, so far as our science can reveal it." The tension between Einstein's cosmic religiosity and traditional religion reflects deeper philosophical questions about religion's nature and function. Traditional religion provides comfort, moral guidance, community, ritual, and answers to existential questions like why suffering exists and what happens after death. Einstein's Spinozistic religion offers none of these things. It provides only intellectual and aesthetic satisfaction in understanding nature. Critics argue that Einstein's cosmic religion is not truly religion at all, merely science wrapped in religious language. Religion inherently involves relationship with the divine, worship, prayer, and faith beyond reason. Einstein's position strips away everything distinctive about religion, leaving only wonder at nature. Why call this religion rather than simply philosophical naturalism? Defenders respond that Einstein captured something essential about religious experience. The sense of encountering something immeasurably greater than ourselves, something that evokes awe and humility. Traditional religion anthropomorphizes this experience, projecting human qualities onto the transcendent. Einstein's cosmic religion preserves the core experience while eliminating primitive anthropomorphism. Einstein himself argued that cosmic religiosity represents religion's most mature form. He traced religious evolution through 3 stages. First, fear-based religion arises from terror of natural forces and desire for protection. Primitive peoples worship storms, fertility, and death as gods. Second, moral religion emerges when people conceive God as lawgiver and judge who rewards virtue and punishes vice. This stage includes traditional Judaism, Christianity, and Islam. Third, cosmic religion transcends fear and morality to embrace pure wonder at existence itself. According to Einstein, humanity needs to progress beyond moral religion to cosmic religion. Moral religion breeds dangerous fanaticism because believers think they know God's will and can impose it on others. Religious wars, inquisitions, and persecution result from moral religion's confidence that God takes sides in human disputes. Cosmic religion eliminates such dangers because it locates the divine in nature's impersonal laws, not in human affairs. This evolutionary view of religion has been criticized as culturally arrogant. Einstein essentially claimed that his philosophical position represents humanity's religious maturity, while traditional believers remain primitive. Critics point out that this dismisses billions of people's genuine religious experiences as childish. It also ignores religion's social and psychological functions, focusing only on cognitive content. Moreover, Einstein's cosmic religion faces philosophical problems. If God equals nature, and nature operates deterministically according to physical law, then everything that happens, including evil and suffering, occurs necessarily as part of God. This makes God responsible for everything, both good and bad. Traditional theology addresses this problem of evil by giving God purposes and humans free will, so that suffering results from creaturely freedom or serves divine purposes. Einstein's God has no purposes, and humans have no freedom. Evil becomes simply part of nature's necessary unfolding, which seems morally inadequate. Einstein acknowledged this difficulty, but offered no solution. He wrote about the agonizing problem of evil and confessed he found no satisfactory answer. Some suffering serves evolutionary purposes, strengthening species through natural selection. But much suffering seems pointless and excessive. If the universe embodies perfect rationality, why does it contain so much apparent irrationality in the form of waste, cruelty, and pain? Traditional theodicy, which means justifying God's goodness despite evil, relies on free will or inscrutable divine purposes. Einstein rejected both options. He denied libertarian free will, which we will discuss further in Part 8. And he rejected appeals to mysterious divine purposes as intellectual dishonesty. This left the problem of evil unresolved within his worldview. Another challenge concerns cosmic religion's motivational power. Traditional religion motivates moral behavior through promises of reward and threats of punishment, or through relationship with a loving God who commands virtue. Einstein's cosmic religion offers no such motivation. Why should contemplating nature's mathematical elegance make someone behave ethically? Einstein believed that cosmic religious feeling naturally produces ethical behavior because it diminishes selfish ego and cultivates humility. Recognizing our tiny place in the vast cosmos makes personal desires seem petty. We identify with the whole rather than fixating on narrow self-interest. This generates compassion and moral concern. Critics remain unconvinced. Many scientists experience cosmic wonder without becoming especially ethical. Many traditional believers act morally without cosmic religiosity. The connection Einstein drew between contemplating nature and ethical behavior seems contingent rather than necessary. Einstein's religious views also influenced his approach to Zionism and Judaism. Though not religiously observant, Einstein identified culturally and ethically with Judaism. He supported the Zionist project of establishing a Jewish homeland in Palestine. But he opposed Jewish religious nationalism and worried that the state of Israel would become theocratic. He advocated for Arab-Jewish cooperation and a binational state rather than exclusively Jewish sovereignty. His vision reflected his broader religious philosophy, emphasizing universal human values and rational cosmopolitanism over tribal allegiances and religious particularism. Einstein saw Judaism's value in its ethical teachings and intellectual traditions, not in claims to divine election or sacred land. The contemporary relevance of Einstein's religious views appears in ongoing debates about science and religion's relationship. Some argue they are incompatible because science assumes naturalism while religion assumes supernaturalism. Others claim they address different questions. Science explains how nature works, while religion addresses meaning and values. Einstein's position challenges both views. Against incompatibility, he shows that scientific practice can be religiously motivated if we define religion broadly enough. Against separation, he argues that cosmic structure itself has religious significance, not merely human meanings projected onto it. Modern physics has only deepened the mysteries that inspired Einstein's cosmic religiosity. The universe began in a Big Bang nearly 14 billion years ago and has been expanding ever since. Why does the universe exist rather than nothing? Why do physical constants have the precise values necessary for life? These anthropic questions revive ancient theological debates in cosmological form. Some physicists propose a multiverse, countless universes with different physical laws, so our life-permitting universe is not surprising, but statistically inevitable. Others see fine-tuning as evidence for design or purpose in nature. Einstein would likely have rejected both explanations, the multiverse as unfalsifiable speculation and design as anthropomorphic projection. But these debates continue the religious impulse to find ultimate explanation that Einstein embodied. Perhaps Einstein's deepest religious conviction was that the universe should be rationally comprehensible. He could not prove this. Indeed, quantum mechanics seemed to challenge it. But Einstein maintained this conviction as an article of faith, or more precisely, as the foundation of cosmic religiosity. Science rests on the faith that nature follows intelligible patterns discoverable by human reason. This raises a final question. Is Einstein's cosmic religion actually religious, or is it philosophy using religious vocabulary? The answer depends on how broadly we define religion. If religion requires supernatural belief, personal deity, worship practices, and moral commandments, then Einstein's views fall outside religion entirely. If religion encompasses any response to ultimate reality that evokes awe, reverence, and commitment to truth beyond self-interest, then Einstein was genuinely religious in his own way. Einstein himself thought the distinction mattered less than the underlying attitude. What mattered was cultivating the cosmic religious feeling, the sense of participating in something infinitely greater than ourselves, something both terrible and beautiful that demands our intellectual and moral seriousness. Whether we call this religion or philosophy, it motivated Einstein's scientific work and shaped his ethical commitments. It remains one expression, perhaps the most intellectually sophisticated expression, of humanity's perennial religious impulse to find meaning in confronting the cosmos. Part 5. The Nature of Time, Block Universe, Arrow of Time, and the Present Moment. Einstein's relativity forced radical reconceptualization of time's nature. The implications extend far beyond physics into philosophy, consciousness studies, and our basic understanding of human existence. If relativity is correct, then much of our intuitive understanding of time is mistaken. The past, present, and future may not be what they seem. Relativity implies what philosophers call the block universe, or eternalism. Imagine all moments of time, past, present and future, existing simultaneously in a four-dimensional space-time block. Your birth, your current reading of these words, and your eventual death all exist equally, located at different positions in time, just as different locations exist simultaneously in space. Nothing comes into existence or passes out of existence. Everything simply exists at its space-time location. This view contradicts presentism, the common-sense belief that only the present moment exists. According to presentism, the past no longer exists, and the future does not exist yet. Only now is real. But relativity shows that simultaneity is relative to the observer. Different observers disagree about which distant events are happening now. If observers cannot agree on what constitutes the present moment, how can only the present be real? The philosopher Hilary Putnam formalized this argument. Consider two observers moving relative to each other. Events simultaneous for one observer occur at different times for the other. If reality consists only of what exists now, then the two observers inhabit different realities. But this seems absurd. Reality should not depend on one's motion. The only solution is that all moments exist equally, forming the four-dimensional block universe. Einstein himself endorsed this view, though his statements were sometimes ambiguous. When his dear friend Michel Besso died in 1955, Einstein wrote a consoling letter to Besso's family. He said, "For us believing physicists, the distinction between past, present and future is only a stubbornly persistent illusion. This suggests Einstein accepted the block universe and rejected the special reality of the present moment. The philosophical implications are staggering. If the future already exists, then it seems to be fixed and unchangeable. Everything that will happen is already real at future space-time coordinates. This appears to eliminate human agency and make the future predetermined. Our sense that we can influence future outcomes becomes illusory. Defenders of the block universe respond that this conflates existing with being unchangeable. In the block universe, your choices exist just as much as any other events. Your decision-making is part of the space-time structure. The fact that your choice exists at a particular space-time location does not mean it was determined by earlier events. The block universe is compatible with both determinism and indeterminism. But critics maintain that the block universe still seems to eliminate genuine becoming and change. Change involves something coming into existence that previously did not exist. If everything exists eternally in the block, nothing truly becomes. We seem to experience time flowing, the present advancing from past toward future. The block universe renders this experience illusory. This raises the hard problem of time's passage. Why do we experience time as flowing if time is actually static like space? Why does consciousness seem to move through the block universe, rather than existing simultaneously at all moments? Philosophers offer various answers, none fully satisfying. Some argue that consciousness necessarily experiences the block sequentially because mental states require time to process information. Your brain at one moment accesses memories of earlier brain states, creating the subjective sense of passage. But this does not explain why we experience time flowing in one direction, from past to future, rather than randomly or backward. The arrow of time, the asymmetry between past and future, poses another deep puzzle. Physical laws at the fundamental level are time-symmetric, working equally well forward or backward. If you watch a film of subatomic particles interacting and run it backward, you cannot tell which direction is correct. Both directions obey the laws of physics. Yet our experience shows radical asymmetry. We remember the past, but not the future. We can influence the future, but not the past. Effects follow causes in one temporal direction, not the reverse. Eggs break, but do not spontaneously reassemble. Living organisms age and die, but never age backward to youth. This asymmetry arises from thermodynamics, the physics of heat and energy. The second law of thermodynamics states that entropy, meaning disorder or randomness, always increases in closed systems. Orderly configurations spontaneously evolve toward disorder, but disorder never spontaneously organizes itself. Ice melts into water, but water does not spontaneously freeze without external intervention. The entropy increase defines time's arrow. The past is the direction of lower entropy. The future is the direction of higher entropy. Our memories work forward through time because memory formation requires creating ordered structures in brains, which increases entropy elsewhere, consistent with time's arrow. But this raises a puzzle. Why was entropy so low in the universe's past? The Big Bang began in an extraordinarily ordered, low-entropy state. Ever since, entropy has been increasing, and this increase makes time's arrow possible. But why did the universe start with low entropy? This seems to require special initial conditions that appear fine-tuned and unexplained. Einstein's relativity does not solve the entropy problem, though it provides the framework within which the question arises. General relativity describes space-time geometry and gravity, but says nothing about why entropy increases. The arrow of time remains one of physics' great unsolved problems. Another temporal puzzle concerns the specious present, the experience now that seems to have duration. The present moment does not feel like a mathematical instant of zero duration. It seems to last perhaps a few seconds. We experience a specious present, a thick now containing immediate past and incipient future. How does this subjective temporality relate to physical time? Neuroscience shows that consciousness requires integration of information across time. Your brain combines sensory inputs arriving at slightly different times, compares them to recent memories, and generates predictions about immediate future. This neural processing creates the experience now, but this explains how we generate temporal experience, not what temporality is in the physical world. The philosopher Adolf Grünbaum argued that the specious present shows that passage is purely psychological. Physical time consists of a linear sequence of instantaneous moments. Passage occurs only in consciousness as the brain processes information sequentially. Time itself does not flow. We flow through time, or more accurately, our conscious states exist at successive time slices and remember earlier states. Others maintain that passage must be objective because change requires time's passage. An object moving from here to there must traverse intermediate locations sequentially. This seems to require objective becoming, not merely subjective experience. Perhaps relativity reveals that time is more spatial than previously thought, but some residual becoming remains necessary for change. These debates connect to quantum mechanics' measurement problem. When does the quantum wave function collapse? Does collapse happen at a specific instant? And if so, how do we identify that instant given relativity's denial of absolute simultaneity? Some physicists propose that consciousness causes collapse, which would make time's passage essential to quantum mechanics. Others deny that collapse happens at all, supporting the many worlds interpretation where the block universe contains all quantum branches. Einstein remained largely silent on these philosophical puzzles about consciousness and temporality. He accepted that the present moment is conventional rather than absolute, and he endorsed the block universe view. But he did not deeply engage questions about subjective time experience or the relationship between physics and phenomenology. The physicist Lee Smolin has recently challenged the block universe view, arguing that time is fundamental and real. Smolin claims that physics has been misled by treating time like space. Time is qualitatively different because only present exists, and becoming is real. He proposes that quantum mechanics' indeterminism reflects genuine ontological openness of the future. The future does not exist yet because it has not been created yet. Smolin's position revives presentism using quantum mechanics against relativity's eternalism. If quantum outcomes are truly indeterminate until they occur, then the future cannot already exist in the block universe. The block universe picture assumes determinism, or at least that all possibilities exist in some sense. But if the future is genuinely open, only the present exists, and the block universe is wrong. Critics respond that Smolin's argument fails. The block universe is compatible with indeterminism. Future quantum events exist at their space-time locations without being determined by the past. Randomness does not require presentism. Additionally, relativity's evidence for eternalism is overwhelming, while Smolin's presentism struggles to account for relativity's empirical success. The debate illustrates how Einstein's work generated questions extending far beyond his direct concerns. He transformed time from an obvious intuitive concept into a deep mystery requiring philosophical clarification. Nearly a century later, physicists and philosophers still disagree about what time is and whether our experience of temporal passage corresponds to anything in physical reality. Time's nature also affects questions about personal identity and death. If the block universe is correct, then in a sense you never cease to exist. Your life exists eternally at its space-time location. Death means reaching the temporal endpoint of your world line, the path through space-time that constitutes your life. But your earlier temporal stages continue existing just as permanently as spatial locations continue existing after you leave them. Some find this consoling, suggesting death is less tragic if our lives exist permanently in the space-time block. Others find it cold comfort. What matters emotionally is that we experience consciousness sequentially, and death ends our sequence. Whether our lives exist timelessly elsewhere in the block seems irrelevant to the lived experience of mortality. Einstein's own attitude toward death reflected his block universe view. He wrote about death with equanimity, even serenity, unusual for someone not religiously committed to an afterlife. He described individuals as transient expressions of the larger cosmos, like waves on the ocean. Waves rise and fall, but the ocean persists. Similarly, individuals come and go, but the cosmos endures. This perspective gave Einstein acceptance of mortality without requiring supernatural beliefs. Whether this attitude is psychologically available to most people remains questionable. Einstein combined extraordinary intellectual understanding with unusual emotional detachment. His cosmic perspective on death might work for rare individuals, but not provide general consolation. The contemporary cutting edge concerns quantum gravity, the still undiscovered theory unifying quantum mechanics and general relativity. Various approaches to quantum gravity suggest that time itself might be emergent rather than fundamental. At the most basic level, perhaps there is no time, only timeless quantum states. Time emerges at larger scales through quantum processes we do not yet understand. If time is emergent, many puzzles might dissolve. The question of what time is would be like asking what temperature is. Temperature emerges from molecular motion but is not fundamental. Similarly, time might emerge from timeless quantum reality. Questions about time's passage and the present moment might reflect our perspectival access to reality rather than reality's fundamental structure. These speculations remain controversial and experimentally untested, but they show how Einstein's relativistic revolution continues generating new questions and theoretical possibilities. Time, which seemed obvious and unproblematic before Einstein, has become one of physics' deepest mysteries. We use time constantly, yet cannot definitively say what it is, whether it passes, or whether the present moment has any objective reality. Part 6. The Unification Dream. His Quest for a Theory of Everything. Einstein's final 30 years focused on one all-consuming goal: discovering a unified field theory that would explain all physical forces through a single mathematical framework. He never succeeded. Many physicists considered this quest a tragic waste of his genius. Yet Einstein's unification program shaped modern physics' research agenda and raised profound questions about scientific explanations' ultimate aims. The unification impulse drove Einstein's greatest successes. Special relativity unified space and time into space-time. General relativity unified gravity with geometry. Einstein believed unification represented genuine progress, not mere mathematical convenience. If apparently distinct phenomena derive from common principles, we have achieved deeper understanding. By the 1920s, physics recognized four fundamental forces. Gravity attracts masses. Electromagnetism governs electric charges and magnetic fields. The strong nuclear force binds atomic nuclei. The weak nuclear force causes radioactive decay. Einstein wanted to show these were aspects of a single unified field. His strategy focused on unifying gravity and electromagnetism first, since these were the only forces understood in his time. He tried extending general relativity's geometric approach to include electromagnetism. If gravity is space-time curvature, perhaps electromagnetism is some other geometric property of space-time, like torsion or additional dimensions. Einstein explored dozens of mathematical frameworks over 3 decades. He would develop a theory, work intensely on it for months or years, publish promising results, then abandon it when problems emerged. Colleagues sometimes joined briefly, but usually left when Einstein's stubbornness about quantum mechanics became clear. He insisted that a correct unified theory must be deterministic and classical, not probabilistic and quantum. This requirement doomed Einstein's program. By the 1930s, quantum mechanics had proven essential for understanding atoms, molecules, and radiation. The electromagnetic force is fundamentally quantum mechanical. Any unification ignoring quantum mechanics could not succeed. Einstein recognized this but refused to compromise his philosophical principles. He believed quantum mechanics was incomplete and would eventually be replaced by a deterministic theory. His unified field theory would provide that replacement he hoped, showing how quantum phenomena emerge from deeper classical laws. This strategy failed completely. Einstein produced no testable predictions from his various unified theories. Most collapsed under mathematical scrutiny. Meanwhile, quantum mechanics continued accumulating spectacular successes, and physics advanced rapidly in directions Einstein ignored. Why did Einstein persist despite repeated failure and scientific isolation? Several factors combined. First, his enormous early success convinced him his intuitions were reliable. He had revolutionized physics twice by trusting reason over convention. Perhaps he could do it again. Second, Einstein's philosophical commitments to realism, determinism and rationality made quantum mechanics unacceptable as fundamental physics. If quantum mechanics was here to stay, Einstein would work towards something better rather than accept its indeterminism and observer dependence. Third, Einstein believed strongly in nature's unity. The universe exhibits remarkable order and intelligibility. This suggests a unified explanation rather than unrelated laws governing different phenomena. Aesthetic considerations influenced Einstein profoundly. He found quantum mechanics ugly in its apparent disunity and reliance on mysterious measurements. Fourth, Einstein trusted mathematical beauty as a guide to truth. He believed that correct theories should be mathematically elegant and inevitable feeling. Some of his unified field theories had this quality, even though they made no predictions. Einstein hoped that working purely from mathematical structure might reveal physical truth. All these reasons made sense given Einstein's previous success and philosophical worldview. But they led him astray. Physics in the mid-20th century required engagement with experimental data and quantum mechanics, not pure mathematical speculation based on classical prejudices. Contemporary physicists learning about Einstein's later work often feel puzzled or disappointed. How could someone so brilliant waste decades on obviously doomed projects? Why did he not recognize that quantum mechanics was here to stay? These questions miss something important about scientific risk-taking and philosophical integrity. Einstein could have spent his later years working on incremental problems within mainstream physics, where his contribution would have been solid but not revolutionary. Instead, he gambled everything on a program he considered more important, even though success seemed unlikely. The gamble failed, but perhaps the attempt itself has value independent of success. Moreover, Einstein's unification program, though unsuccessful, established the research agenda that produced modern physics' greatest achievements. Today's standard model of particle physics unifies electromagnetism with the weak and strong nuclear forces using quantum field theory. This achievement vindicates Einstein's intuition that unification is possible and desirable, though it requires accepting quantum mechanics rather than replacing it. The standard model leaves gravity unincorporated, however. Gravity remains described by Einstein's general relativity, a classical theory incompatible with quantum mechanics at extreme scales. Theoretical physicists still pursue Einstein's dream of unifying all forces, now called a theory of everything. Several approaches compete today. String theory proposes that fundamental entities are not point particles, but tiny vibrating strings. Different vibration patterns correspond to different particles and forces. String theory naturally includes gravity and potentially unifies all forces in a quantum framework. However, it requires extraspatial dimensions beyond the three we observe and makes no testable predictions yet. Loop quantum gravity takes a different approach, quantizing spacetime itself. It treats spacetime geometry as fundamentally discrete at the smallest scales rather than continuous. This resolves certain infinities plaguing quantum gravity, but struggles to incorporate other forces. Both approaches face serious criticisms. They lack experimental evidence despite decades of theoretical development. They are mathematically complex and require assumptions about unobserved physics. Some physicists argue they repeat Einstein's mistake, pursuing mathematical elegance and unification without empirical guidance. Philosopher Nancy Cartwright has influentially argued that physics does not actually tend toward unified laws. Instead, she claims, we have a patchwork of domain-specific theories that work well in limited contexts, but do not combine into a unified whole. The search for fundamental unity might be a metaphysical prejudice rather than reasonable scientific expectation. Defenders of unification respond that history shows repeated, successful unifications. Newton unified terrestrial and celestial mechanics. Maxwell unified electricity and magnetism. Einstein unified space and time, then unified gravity with geometry. The Standard Model unified three forces. Why should unification stop now? But Cartwright's critique challenges whether these were genuine unifications or merely showed that different phenomena follow similar mathematical patterns. Does showing that electricity and magnetism share a common mathematical description prove they are fundamentally one thing, or merely that our mathematics can describe both? This philosophical question underlies debates about string theory and other unification programs. Are physicists discovering nature's unified structure, or imposing unity through mathematical frameworks that may be convenient but not uniquely true? Einstein would have sided firmly with realism about unification. He believed the universe really is unified at its deepest level, and physics' job is discovering that unity. Mathematical description is not merely convenient, but approximately true representation of nature's structure. Yet Einstein's own failure might count against this view. His unified field theories were mathematically elegant but physically sterile. They proved that mathematical beauty alone, without empirical constraint, leads nowhere. Contemporary string theory faces similar criticisms. It offers mathematical elegance and potential unification, but no testable predictions distinguishing it from alternatives. Some physicists worry that string theory has become a mathematical game disconnected from physical reality, repeating Einstein's later career pattern. The deeper issue concerns scientific explanation's ultimate goal. Should physics seek a final theory, a complete mathematical description from which everything else follows? Or should it remain content with effective theories that work well in limited domains without claiming fundamental truth? Einstein firmly believed in the final theory possibility. He thought the universe must be comprehensible to human reason in principle, even if the final theory remains undiscovered. This faith motivated his unification quest and gave his life meaning despite repeated failure. But perhaps this faith is unjustified. Maybe the universe is not actually unified at the deepest level. Maybe different domains require genuinely different physics, with no common foundation. Or maybe unification exists, but is too complex for human minds to grasp. We might lack the intellectual capacity to understand everything, just as dogs cannot understand relativity. These possibilities challenge the Enlightenment conviction, which Einstein embodied, that human reason can comprehend reality fully. If nature is ultimately incomprehensible, then Einstein's unification quest was not merely unsuccessful, but impossible in principle. Einstein's response would be that we cannot know without trying. Perhaps complete understanding is impossible, but we cannot discover this by giving up. We must pursue unification as far as possible, and only failure to make progress despite genuine effort would justify skepticism. This pragmatic response has merit. Even if ultimate unification proves impossible, the attempt generates valuable insights. Einstein's failed unified theories taught later physicists what does not work. Similarly, string theory and loop quantum gravity, even if ultimately unsuccessful, advance our understanding of quantum gravity's requirements and constraints. The other legacy from Einstein's unification program concerns the role of experiment in theoretical physics. Einstein's greatest successes came from thought experiments and mathematical reasoning ahead of empirical data. This encouraged him to continue theorizing without experimental guidance in his later work. But the strategy that worked brilliantly for relativity failed completely for unification. This raises questions about scientific methodology. When should physicists pursue speculative theories without experimental evidence? How long should they persist before admitting failure? Einstein's career suggests no simple answers. Sometimes speculation succeeds spectacularly. Sometimes it fails completely. Distinguishing productive speculation from wasted effort remains difficult. Perhaps the key difference is whether speculation connects to empirical phenomena even indirectly. Special and general relativity, though based on thought experiments, addressed real puzzles, the behavior of light and the nature of gravity. Einstein's unified field theories lacked comparable empirical anchoring. They were purely mathematical constructions, hoping to eventually connect to reality. Contemporary unification programs face similar challenges. String theory began addressing real problems like quantum gravity and black hole thermodynamics. But it has expanded into a vast mathematical landscape of possibilities without clear empirical selection criteria. Critics argue it has lost touch with experiment. Defenders respond that the questions are so fundamental that standard experimental approaches cannot apply, requiring theoretical exploration to identify what experiments might eventually test. Einstein's unification quest thus raises deep questions about how science should proceed when addressing the most fundamental questions. Standard scientific method involves propose hypotheses, test experimentally, refine or reject based on results. But this cycle breaks down for theories of everything that potentially explain the entire universe. You cannot do controlled experiments on the whole universe. Alternative standards become necessary. Mathematical consistency, explanatory power, unification of previously separate domains, novel predictions, even if currently untestable. Einstein relied on these standards throughout his career. They worked sometimes, failed other times. We still lack reliable methods for judging purely theoretical work in fundamental physics. Part 7. Political Philosophy, Pacifism, Socialism, World Government, and Zionism. Einstein's political philosophy emerged from the same values underlying his physics: rationality, universalism, and belief in humanity's capacity for moral progress. He engaged actively in political causes throughout his life, often controversially, applying his intellectual authority to advocate for radical social transformation. His political views reflected deep philosophical commitments about human nature, justice, and the proper organization of society. Einstein described himself as a democratic socialist and a pacifist, though both positions evolved considerably through his life. He believed capitalism inevitably produces inequality, exploitation and war because it concentrates wealth and power in private hands. Economic competition between capitalist nations for resources and markets generates international conflicts. Only by abolishing private ownership of production means could humanity achieve lasting peace and justice. This sounds like orthodox Marxism, but Einstein rejected Marxist materialism and determinism. He did not believe economic structures alone determine everything about society, nor did he think communism would inevitably replace capitalism through historical necessity. Rather, Einstein argued that humans must consciously choose to create just economic arrangements guided by moral principles. Socialism was an ethical imperative, not an inevitable outcome. Einstein outlined his socialist vision in a 1949 essay called Why Socialism? He argued that capitalism produces an oligarchy controlling production and distribution, mass media, education and politics. This concentration of power corrupts democracy, reducing it to a facade while actual decisions serve elite interests. Workers become commodities, their labour bought and sold, alienating them from their work and from each other. The solution required socializing production means through democratic planning. Rather than market competition determining what gets produced, society would collectively decide based on human needs. This would eliminate unemployment, poverty, and the boom-bust cycles inherent to capitalism. It would free humans to develop their capacities fully rather than subordinating everything to profit. Critics raised obvious objections. Who decides what society needs? How does democratic planning avoid bureaucratic tyranny? The Soviet Union claimed to practice socialism but created totalitarian dictatorship with secret police, labor camps, and mass murder. How would Einstein's democratic socialism avoid similar outcomes? Einstein acknowledged these problems, but never developed detailed institutional proposals. He rejected Soviet communism as state capitalism that merely replaced private capitalists with party bureaucrats. True socialism required genuine democracy, civil liberties, and decentralization. But Einstein remained vague about mechanisms ensuring these values. This vagueness reflected Einstein's approach to political philosophy generally. He focused on identifying moral imperatives rather than institutional details. Capitalism was unjust because it permitted exploitation and inequality. Therefore, humanity must transcend capitalism, even without a complete blueprint for what comes after. Some philosophers criticize this approach as irresponsible utopianism. Good intentions without realistic implementation plans often produce disasters, as communist regimes demonstrated. Einstein's democratic socialism might be impossible to realize, and attempting it might generate tyranny worse than capitalism's injustices. Defenders respond that moral vision matters even without perfect implementation strategies. Einstein correctly identified capitalism's failings. Whether his socialist alternative would work remains untested, since no society has tried genuine democratic socialism as Einstein conceived it. Einstein's pacifism was equally controversial and evolved significantly. He initially embraced absolute pacifism, refusing all military service and advocating total disarmament. During World War I, Einstein signed pacifist manifestos and denounced nationalism as primitive tribalism. He believed war resulted from irrational group psychology and could be eliminated through moral education and international cooperation. This position reflected Einstein's cosmic perspective. From the viewpoint of the universe, national boundaries and ethnic identities are arbitrary and insignificant. Humanity should identify with the species as a whole rather than particular nations or groups. War is collective insanity, sacrificing individual lives for abstractions like national honor. However, the rise of Nazism forced Einstein to reconsider. In 1933, Hitler took power in Germany. Nazi ideology explicitly promoted racism, militarism, and conquest. Jews faced persecution, violence, and eventually genocide. Could pacifism respond adequately to such evil? Einstein reluctantly concluded it could not. He had fled Germany and renounced his citizenship upon Hitler's rise. From exile, Einstein recognized that Nazi Germany could only be stopped by military force. He wrote publicly abandoning his earlier pacifism and supporting military preparation against fascism. This reversal troubled Einstein deeply. It seemed to admit that violence is sometimes necessary and that moral principles cannot always guide politics. Einstein never returned to absolute pacifism, but considered this one of his life's great disappointments. He had hoped human reason could progress beyond war, but history appeared to prove him wrong. The atomic bomb created another moral crisis for Einstein. In 1939, physicists discovered nuclear fission, releasing enormous energy from splitting atoms. Refugee scientists who had escaped Nazi Germany feared Hitler would develop atomic weapons. They convinced Einstein to sign a letter to President Roosevelt warning of this danger and urging American development of atomic bombs. Einstein's signature carried enormous prestige and helped launch the Manhattan Project that created the first atomic bombs. The United States dropped 2 atomic bombs on Japan in 1945, killing approximately 200,000 people and ending World War II. Einstein later called signing the letter his greatest mistake, though he acknowledged the threat from Nazi Germany was real. After the war, Einstein devoted enormous energy to nuclear disarmament and world government. He argued that national sovereignty had become obsolete in the atomic age. Giving individual nations the power to build nuclear weapons guaranteed eventual catastrophe. Human nature being what it is, some nation would eventually use nuclear weapons in war, potentially destroying civilization. The only solution was creating a world government with monopoly on military force, especially nuclear weapons. National militaries would be abolished or reduced to police forces. International disputes would be resolved through law rather than war. This required nations surrendering some sovereignty to global institutions, which Einstein acknowledged would face fierce resistance. Critics called this naive and dangerous. A world government powerful enough to prevent war would be powerful enough to impose tyranny globally. Who would control this government? What would prevent it from becoming a totalitarian world state? Einstein's proposal seemed to risk replacing national conflicts with global dictatorship. Einstein recognized these dangers, but considered them lesser evils than nuclear annihilation. He proposed that the world government should have limited powers focused on preventing war, not total sovereignty over all matters. Democratic procedures and constitutional limits would prevent tyranny. But again, Einstein provided few institutional details. His world government proposal reflects broader philosophical tensions in Einstein's political thought. He valued individual freedom highly and opposed totalitarianism. Yet his proposals for socialism and world government required concentrating significant power in collective institutions. How could such concentration avoid abuse? Einstein's answer relied on moral progress and rational education. He believed humans could learn to cooperate rather than compete, to identify with humanity rather than narrow groups. Creating just institutions required first creating just people through education emphasizing reason, compassion, and universal values. This optimism about human nature seems questionable given historical evidence. Humans have perpetrated horrific violence throughout history despite education and moral teaching. Perhaps competitive tribal instincts are too deeply embedded in human nature to overcome through reason alone. Evolutionary psychology suggests that humans evolved to compete for resources, favor their own group, and distrust outsiders. These tendencies made evolutionary sense in ancestral environments, but create problems in modern societies with nuclear weapons and global interdependence. Overcoming them might require more than moral education, perhaps fundamental changes to human biology or artificial constraints on human behavior. Einstein rejected biological determinism, however. While acknowledging humans have aggressive tendencies, he insisted culture and reason could override them. Human nature is plastic enough that different social arrangements produce dramatically different behavior. The challenge is creating institutions that nurture humanity's better angels rather than its demons. Einstein's Zionism exemplified tensions in his political philosophy. Though culturally Jewish and supportive of Jewish welfare, Einstein rejected religious Judaism and Jewish nationalism. He supported establishing a Jewish homeland in Palestine, primarily for practical reasons. Jews faced persecution globally and needed a safe refuge. But he opposed creating an exclusively Jewish state with Jewish political sovereignty. Einstein advocated for a binational state where Jews and Arabs shared power equally. He warned that Jewish nationalism would perpetuate the very tribal thinking he opposed in all forms. Treating Arabs as enemies or inferiors would betray Jewish ethical traditions and create endless conflict. Only cooperation and mutual respect could produce lasting peace. These views put Einstein at odds with mainstream Zionism. Most Zionist leaders wanted a Jewish state with Jewish majority rule. They considered Einstein's binationalism naive and dangerous, conceding too much to Arabs who might use power sharing to undermine Jewish security. Einstein responded that security through domination is illusory and that only justice produces genuine safety. After Israel's establishment in 1948, Einstein supported its existence but criticized its policies toward Arabs. He opposed territorial expansion, military actions against civilians, and laws discriminating against non-Jewish citizens. He declined an offer to become Israel's second president in 1952, partly because he disagreed with government policies. Einstein's position reflects his consistent universalism. No group deserves special privileges based on ethnicity or religion. Jewish suffering does not justify causing Arab suffering. The proper response to persecution is not establishing Jewish dominance, but creating societies based on equal rights for all. Critics argue that Einstein's universalism ignored political realities. Jews had faced 2 millennia of persecution culminating in the Holocaust. A state providing safe haven and self-determination seemed morally justified, even if imperfect. Einstein's binational alternative might have been impossible, given Arab rejection of any Jewish presence. Defenders respond that Einstein identified principles that remain relevant. Israel's ongoing conflict with Palestinians stems partly from treating it as an ethnic conflict between Jews and Arabs, rather than a human rights issue. Einstein's emphasis on universal values and equal dignity might have prevented decades of violence if adopted. The tension between group identity and universal values appears throughout Einstein's political thought. He valued Jewish cultural traditions, but rejected Jewish particularism. He supported democratic socialism, but opposed Soviet communism's totalitarian implementation. He advocated world government, but feared global tyranny. These tensions reflect a deeper philosophical problem. Can universal values actually guide political action, or must politics always compromise between competing particular interests? Einstein believed reason could identify universal principles: human equality, individual freedom, social cooperation. Politics should realize these principles through appropriate institutions. Realists in political philosophy argue this approach misunderstands politics' nature. Politics concerns power: who has it, how they obtained it, how they use it. Moral principles matter, but cannot override power considerations. Successful politics requires strategic calculation, compromise, and sometimes moral sacrifice. Einstein rejected political realism as cynical surrender. Yes, politics involves power, but power should serve justice rather than simply perpetuating itself. Treating power as independent of morality corrupts politics and produces tyranny. The challenge is not abandoning moral principles, but finding strategies to implement them despite power constraints. Contemporary political philosophy remains divided on these questions. Liberal philosophers like John Rawls argue that political institutions should be justified through principles everyone could rationally accept, similar to Einstein's universalism. Communitarian critics respond that universal principles ignore how deeply people are shaped by particular communities and traditions. Realist theorists maintain that power politics inevitably dominates despite moral ideals. Einstein's political activism also raises questions about scientists' public roles. Should scientists use their authority from scientific expertise to advocate political positions? Einstein believes scientists have special responsibility to guide society because they understand reason's power and nature's unity. Scientific thinking promotes clarity, skepticism of authority, and concern for evidence, which politics desperately needs. Critics argue that scientific expertise does not translate to political wisdom. Understanding physics does not make someone qualified to judge economic systems, political institutions, or cultural conflicts. Einstein's political pronouncements sometimes displayed naivete about political realities and institutional constraints. His scientific genius did not make him a political genius. Defenders respond that Einstein's universal perspective, trained by scientific cosmopolitanism, gave him valuable political insights even if he lacked policy expertise. His warnings about nuclear weapons and nationalism proved prescient. His emphasis on universal human values remains morally compelling, even if politically difficult to implement. The question remains relevant as contemporary scientists increasingly engage politically on issues like climate change, artificial intelligence, and biotechnology. Should they stick to providing technical information or actively advocate for particular policies? Einstein's example suggests that scientists not only can but should engage politically when their expertise is relevant, while acknowledging the limits of their authority outside their technical domains. Einstein's political legacy is mixed. His democratic socialism never materialized, and contemporary capitalism has only intensified since his time. His world government proposal went nowhere, and nationalism remains powerful. His vision for binational coexistence in Palestine was rejected, and Israeli-Palestinian conflict continues. Yet Einstein's political philosophy retains influence through its articulation of universal humanistic values. His insistence that humans can transcend tribal loyalties, that reason should guide politics, and that justice matters more than power continues inspiring political idealists. Whether this inspiration is noble but futile utopianism or a necessary corrective to political cynicism remains debated. Part 8. Human Nature and Ethics, Freedom, Responsibility, and Moral Philosophy. Einstein's views on human nature, free will, and ethics reveal deep tensions between his deterministic worldview and his commitment to moral responsibility. He believed physics showed that the universe, including human behavior, is fundamentally determined by natural laws. Yet he also believed humans are morally responsible for their choices and can improve themselves through reason and education. Reconciling these positions required sophisticated philosophical arguments that Einstein only partially developed. Einstein was a committed determinist about human action. He believed that everything a person does results necessarily from prior causes: genetic inheritance, early experiences, social environment, and physical brain states governed by natural law. Given complete knowledge of these factors, one could in principle predict all future actions. Free will in the libertarian sense, meaning the ability to choose otherwise than one actually does given identical conditions, is an illusion. Einstein expressed this view forcefully in his essay, The World as I See It. He wrote, "I do not believe in freedom of will. Schopenhauer's words, 'A man can do what he wants, but not want what he wants,' accompany me in all situations throughout my life." This quote from the philosopher Arthur Schopenhauer captures the determinist position. We experience wanting and choosing, but these mental states themselves arise from causes beyond our control. This position followed from Einstein's scientific worldview. Physics describes nature as a network of causes and effects, operating according to mathematical laws. Humans are part of nature, not exceptions to it. Our brains are physical systems obeying the same laws as everything else. Mental experiences like choosing and deciding are produced by brain processes that are themselves determined by prior physical states. The implications seem to undermine moral responsibility. If people cannot choose otherwise than they do, how can we hold them responsible for their actions? Punishment seems unjust if criminals could not have avoided their crimes. Praise seems undeserved if good people could not have done otherwise. Morality itself appears to rest on a mistake, the belief that people control their choices. Einstein embraced a compatibilist response to this challenge. Compatibilism maintains that free will and moral responsibility are compatible with determinism if we define them correctly. Free will does not require the ability to choose otherwise in identical circumstances. Rather, it requires acting according to one's own desires, values, and reasoning without external coercion or internal compulsion. Consider the difference between someone who commits robbery because they want money versus someone forced to rob at gunpoint. Both actions are determined by prior causes, but only the first acts freely in the relevant sense. The first person's action flows from their own character and desires. The second person's action is externally compelled against their will. Compatibilists argue this is the distinction that matters for moral responsibility. We hold people responsible when their actions reflect their character, values, and reasoning. We excuse actions that result from coercion, mental illness, or other factors that bypass the person's rational agency. Whether the person could have done otherwise in some metaphysical sense is irrelevant. Einstein accepted this compatibilist framework but struggled with its implications. He wrote about feeling compassion for wrongdoers because they are as much victims of causes beyond their control as their victims are. A murderer's violent impulses arose from genetics and upbringing that the murderer did not choose. This should generate understanding rather than hatred. Yet Einstein also insisted that society must punish criminals and structure institutions to encourage good behavior. Punishment serves not to give criminals what they deserve, which makes no sense if they could not have chosen otherwise, but to protect society and deter future crimes. We hold people accountable not because they metaphysically deserve blame, but because accountability promotes better behavior. This consequentialist justification of moral responsibility has been widely adopted in contemporary philosophy and law. We maintain practices of praise, blame, punishment, and reward because these practices produce good outcomes, not because people have mysterious libertarian free will. However, critics argue that consequentialist justification fails to capture something essential about moral responsibility. When we blame someone for wrongdoing, we are not merely trying to modify their future behavior. We are expressing that they violated moral requirements and deserve criticism for doing so. This seems to require that they could have done otherwise, not just that blaming them produces good consequences. Einstein's response would likely be that our intuitive sense that people deserve blame is itself an illusion produced by our ignorance of determinism. Once we fully accept that actions are determined, we should abandon retributive attitudes, the desire to make wrongdoers suffer because they deserve it, while maintaining consequentialist practices that promote good behavior. This view faces the problem that human psychology may not work this way. People naturally feel anger at wrongdoers, gratitude toward benefactors, guilt about their own failings, and pride in their accomplishments. These reactive emotions seem essential to human relationships and social cohesion. Can we maintain them while accepting determinism? Some philosophers argue we cannot. If we truly believe determinism, we would lose the reactive emotions that make moral life meaningful. We might intellectually accept that we should still hold people accountable for consequentialist reasons, but we would not feel the emotional engagement that makes accountability personally significant. Einstein's own emotional life suggests this concern may be overstated. He fully accepted determinism, yet still felt moral indignation at injustice, compassion for suffering, and responsibility for his own actions. He believed that understanding determinism should increase compassion, not eliminate moral emotion entirely. We can feel appropriately toward people's actions, while recognizing that those actions resulted from causes beyond the person's ultimate control. Einstein's ethics extended beyond individual responsibility to social justice and human relations. He believed that humans have innate capacities for both selfishness and compassion, competition and cooperation. Which tendencies dominate depends on social institutions and cultural values. Good societies nurture compassion and cooperation through education and just institutions. This environmental emphasis might seem to contradict determinism, which says that education and institutions are themselves determined and cannot ultimately change what is fated to occur. Einstein would respond that determinism does not make efforts at improvement pointless. Our efforts to improve society are themselves part of the causal chain. They are determined, but nonetheless real causes producing real effects. Think of it this way. Predicting that a ball rolling down a hill will reach the bottom does not make the hill's slope causally irrelevant. Similarly, saying that social reform is determined does not make reform efforts causally ineffective. They are part of how the determined future comes about. Einstein grounded his ethics in what he called cosmic religion, which we examined in Part 4. The sense of belonging to something vastly greater than ourselves, the cosmos itself, naturally produces ethical behavior. When we recognize our insignificance in cosmic perspective, petty self-interest seems absurd. We identify with the whole rather than narrow ego. This parallels Buddhist ethics, which emphasizes transcending selfish ego through recognizing the impermanent, interconnected nature of existence. Einstein never studied Buddhism deeply, but arrived at similar conclusions from his physics and philosophical reflection. Critics question whether cosmic perspective actually motivates ethics. Recognizing our cosmic insignificance might instead produce nihilism. If nothing matters on a cosmic scale, why bother behaving morally? Helping other humans seems as meaningless as helping individual ants when contemplating the universe's vastness. Einstein's response was that cosmic perspective does not diminish human value, but situates it properly. We are tiny parts of the cosmos, but conscious parts capable of understanding and appreciating the whole. This capacity makes human existence remarkable and precious, even if brief. Ethics involves caring for these remarkable conscious beings and the societies that enable them to flourish. Einstein also believed that rationality naturally leads to ethical behavior. He argued that rational reflection shows that harming others ultimately harms oneself because we are interconnected. Violence, exploitation, and injustice create social instability that threatens everyone. Cooperation and mutual aid produce better outcomes for all. This position, similar to social contract theory in philosophy, assumes that rational self-interest converges with morality. If true, we do not need mysterious moral imperatives beyond natural self-interest properly understood. However, many situations arise where individual self-interest conflicts with collective good. Free rider problems occur when individuals benefit by not contributing to collective goods that require everyone's cooperation. Rational individuals might exploit others' cooperation while not cooperating themselves. Without sanctions or moral constraints beyond self-interest, cooperation often breaks down. Einstein acknowledged these challenges but maintained that enlightened self-interest, understanding long-term and indirect consequences, supports cooperation. Additionally, humans have evolved capacities for empathy and fairness that supplement pure self-interest. These capacities make genuine morality possible, not just strategic cooperation. Contemporary moral psychology research supports this view partially. Humans do have innate moral intuitions about fairness, harm, and cooperation. These intuitions evolved because they promoted survival in social groups, but they are often tribal, favouring one's own group over outsiders, and can be overridden by self-interest or ideology. Einstein's hope that education and reason could strengthen moral intuitions and make them universal rather than tribal has proven optimistic. Moral education shows limited effectiveness in producing consistently ethical behaviour. Reason often rationalizes self-interest rather than constraining it. Yet alternatives like moral relativism or nihilism seem worse, abandoning the possibility of moral progress entirely. Einstein's personal ethics emphasized simplicity, honesty, and resistance to social pressure. He lived modestly despite his fame, avoided material accumulation, and spoke truth to power regardless of consequences. He believed that authenticity, being true to oneself and one's values, constitutes ethical life's core. This existentialist element in Einstein's ethics sits somewhat tensely with his determinism. If our characters and choices are determined, what does authenticity mean? Are we not simply being what we must be? Einstein would likely respond that authenticity means acting according to one's own deepest values and reasoning rather than external pressures or superficial desires. Even if these deepest values are themselves determined, acting on them feels different and produces different outcomes than acting on external compulsion. The subjective experience of authenticity matters even if objectively everything is determined. Einstein's ethics also emphasized what he called the merely personal. He argued that excessive focus on personal concerns, reputation, material success, and social status distracts from what truly matters: understanding, creating, and contributing to human welfare. He wrote that striving for personal achievement and recognition is like a pig's life, implying it wastes human potential. This ascetic attitude reflects Einstein's cosmic religion. From a cosmic perspective, personal achievements are insignificant. What matters is participating in the larger project of human understanding and progress. Individual fame and fortune are ephemeral and ultimately meaningless. Critics note that Einstein himself enjoyed fame and used it to advance causes he cared about. His rejection of the merely personal was perhaps not as complete as he claimed. Moreover, completely transcending personal concerns might be psychologically impossible and perhaps undesirable. Personal relationships, accomplishments and projects give life meaning for most people. Einstein's defense might be that he distinguished between healthy personal engagement and neurotic preoccupation with status and recognition. Caring about one's work and relationships is natural and good. Obsessing over how others perceive you and constantly comparing yourself to others is self-destructive. Cosmic perspective helps maintain this balance by preventing personal concerns from becoming all-consuming. The contemporary relevance of Einstein's ethical views appears in debates about moral responsibility in neuroscience and criminal justice. Brain imaging shows that criminal behavior correlates with specific brain abnormalities and that our actions are determined by brain states we do not consciously control. This revives Einstein's question. How should we respond to wrongdoing if it results from deterministic brain processes? Some neuroscientists argue for eliminating retributive punishment entirely and focusing only on rehabilitation and public safety. This reflects Einstein's compatibilist, consequentialist approach to responsibility. Others worry that abandoning retribution would undermine moral order by failing to express appropriate condemnation of wrongdoing. Einstein's view offers a middle path. Maintain practices of accountability because they serve important social functions, but infuse them with compassion rather than vindictiveness. Understand that wrongdoers are shaped by factors beyond their control, but still hold them accountable to encourage better behavior and protect potential victims. His approach also speaks to contemporary debates about inequality and meritocracy. Meritocracy assumes people deserve their achievements because they worked hard and made good choices. But if choices and efforts are determined by genetics and early environment, which people do not choose, then individual achievements are largely luck rather than earned desert. This determinist critique of meritocracy, which Einstein would likely endorse, supports redistributive justice. If success results from fortunate circumstances rather than moral desert, society should share its benefits more equally. The successful should feel gratitude for their good fortune rather than pride in their superiority. The unsuccessful deserve compassion and support rather than contempt. Critics respond that eliminating merit-based rewards would destroy motivation to work and innovate. Even if achievements are determined, treating them as earned and rewarding them produces better outcomes than treating them as mere luck. Einstein's consequentialist response would likely be that we can maintain incentive systems while acknowledging their philosophical limitations. We reward achievement not because people metaphysically deserve rewards, but because doing so encourages valuable activity. This perspective should make us more willing to provide support for those who are less successful, recognizing that they are not morally inferior, but rather less fortunate. Part 9. Where Einstein was wrong. His failures and limitations. No figure in intellectual history is infallible, and Einstein's mistakes illuminate both his brilliance and its limits. Examining where Einstein went wrong reveals the risks of his methodological approach, the limitations of philosophical commitment over empirical evidence, and how even genius can be constrained by temperament and historical context. Some failures were spectacularly wrong, others subtle but significant. All offer valuable lessons about scientific progress and human fallibility. Einstein's rejection of quantum mechanics stands as his most famous and consequential error. As we explored in Part 3, he spent 3 decades arguing that quantum mechanics must be incomplete because it violated his philosophical principles of realism, determinism, and locality. Every experimental test has vindicated quantum mechanics while contradicting Einstein's preferred alternatives. Bell's theorem proved that Einstein's hoped-for local hidden variable theories are impossible. This failure stemmed from Einstein prioritizing philosophical commitment over empirical success. Quantum mechanics made accurate predictions from the beginning. Rather than accepting these results and adjusting his philosophy, Einstein insisted that a theory violating his principles could not be fundamentally true. This represents a methodological mistake, allowing metaphysical preferences to override experimental evidence. Yet the situation is more nuanced than simple stubbornness. Einstein's criticisms forced quantum mechanics defenders to clarify their interpretation and face conceptual problems they might otherwise have ignored. The EPR paper, though intended to show quantum mechanics' absurdity, eventually enabled Bell's theorem and experimental tests that deepened our understanding. Sometimes being wrong in interesting ways advances science more than being conventionally correct. Einstein's cosmological constant represents a different type of error. When Einstein applied general relativity to cosmology in 1917, his equations predicted that the universe should be either expanding or contracting. This contradicted the prevailing belief in a static, eternal universe. Rather than accepting this revolutionary prediction, Einstein added a term to his equations, the cosmological constant, that produced a static universe. In 1929, Edwin Hubble discovered that the universe is indeed expanding, exactly as Einstein's original equations predicted. Einstein called adding the cosmological constant his biggest blunder, throwing away the chance to predict cosmic expansion before any observations. However, modern cosmology has revived the cosmological constant to explain dark energy, a mysterious force causing the universe's expansion to accelerate. Einstein's blunder turned out to describe something real, though for wrong reasons. This shows how even mistakes can accidentally capture truth, and how scientific progress is more complicated than simple right or wrong judgments. The error reveals Einstein's occasional willingness to modify theories for philosophical rather than empirical reasons. He wanted the universe to be static and eternal because this seemed more rational than a universe with temporal beginning or end. This aesthetic judgment, like his rejection of quantum mechanics, shows the dangers of letting philosophical preference override mathematical implications. Einstein's failure to appreciate quantum mechanics' revolutionary potential when he was young represents a more subtle mistake. He discovered the photon in 1905, showing that light behaves as discrete quanta in certain circumstances. But he treated this as a pragmatic calculation device rather than a fundamental reconceptualization of nature. He failed to see that quantum behavior was not an anomaly to be eventually explained away, but a completely new physics requiring different concepts. This blindness is understandable given how radical quantum mechanics truly is, but it shows that even revolutionary thinkers can fail to recognize revolution in their own work. Einstein overthrew Newtonian physics. yet could not accept that quantum mechanics might similarly require abandoning his own conceptual framework. Einstein's attempts at unified field theory, discussed in Part 6, consumed his final 3 decades without producing any testable predictions. This represents perhaps his greatest scientific failure, wasting enormous intellectual energy on an approach that could not succeed because it ignored quantum mechanics. The failure reveals the limitations of pure mathematical speculation without empirical guidance. Einstein's earlier successes in relativity came from addressing real physical puzzles using thought experiments connected to observable phenomena. His unified field work lacked this empirical grounding. He was doing mathematical philosophy rather than physics, hoping beautiful equations would reveal nature's secrets. Critics argue that Einstein should have recognized this mistake and redirected his efforts. By the 1930s, quantum mechanics was clearly here to stay, and Einstein's isolation from mainstream physics was nearly complete. He could have contributed to other areas where his insights would be valuable. Instead, he persisted in a program almost everyone considered doomed. Defenders note that pursuing long-shot revolutionary programs is exactly what Einstein did successfully with relativity. He could not have known in advance that unification would fail. The attempt itself, even if unsuccessful, demonstrates admirable intellectual courage. Science advances through such risky gambles, even when they fail. Einstein's political judgments, discussed in Part 7, sometimes reflected naivete about practical politics. His advocacy for world government failed to address realistic concerns about how such a government would avoid tyranny or gain legitimacy. His support for democratic socialism remained vague about implementation, despite Soviet communism's demonstrated failures. His belief that education and reason could overcome nationalism and militarism proved too optimistic. These failures stemmed from Einstein's cosmic perspective, which clarified ultimate values but obscured messy political realities. From the universe's viewpoint, national boundaries are arbitrary and war is collective insanity. But politics operates at human scale, where national identities feel real and security threats feel urgent. Einstein's philosophical clarity about what should be true sometimes prevented him seeing what actually is true about human nature and society. Einstein's personal life revealed ethical failures despite his philosophical sophistication. He treated his first wife Mileva poorly during their marriage and divorce, showing emotional coldness and prioritizing his work over family responsibilities. He had multiple affairs while married. His relationships with his children were distant and sometimes painful, particularly with his son Edward, who developed schizophrenia. These failures show that intellectual understanding of ethics does not automatically produce ethical behavior. Einstein understood determinism, compassion, and cosmic perspective philosophically, but struggled to apply these insights in intimate relationships. This gap between theoretical understanding and practical application affects most people, even moral philosophers and enlightened physicists. Some critics argue this hypocrisy undermines Einstein's ethical authority. How seriously should we take moral advice from someone who failed to live up to his own principles in important ways? Defenders respond that moral failure is human and does not invalidate correct moral insights. Einstein's personal flaws make him more relatable, not less credible. Einstein's views on race, while progressive for his time, revealed limitations by contemporary standards. He opposed racism and advocated for civil rights, using his celebrity to support African Americans facing discrimination. However, his travel diaries contain some descriptions of Asian peoples that reflect Orientalist stereotypes and cultural chauvinism. He described Chinese people in ways that suggest he viewed them as culturally inferior, though he admired certain aspects of Chinese culture. This shows how even someone committed to universal human values can harbour unconscious biases shaped by their cultural context. Einstein transcended much of the racism common in early 20th century Europe, but not all of it. This reminds us that moral progress is gradual, and that people's blind spots often become visible only in retrospect. Einstein's epistemological confidence, discussed in Part 1, sometimes led him astray. His belief that mathematical beauty and theoretical elegance reliably indicate truth worked brilliantly for relativity, but failed for quantum mechanics and unified field theory. There is no guarantee that the universe is comprehensible to human reason in the way Einstein assumed. Nature might be more messy, contingent, and resistant to elegant unification than his philosophy allowed. Contemporary physics increasingly recognizes this possibility. The Standard Model, while incredibly successful empirically, is considered aesthetically ugly, with too many arbitrary parameters and disconnected forces. String theory attempts to restore elegance, but has produced no testable predictions after decades of development. Perhaps nature at the fundamental level is not elegant by human standards. Einstein's methodological approach of trusting reason and mathematics over experiment worked once in a revolutionary way, but failed when applied repeatedly. This suggests that scientific methodology cannot follow fixed rules. Different problems require different approaches. Sometimes mathematical reasoning ahead of experiment succeeds spectacularly, as with relativity, and sometimes it leads nowhere, as with unified field theory. Judging when to use which approach requires wisdom that cannot be formalized. Einstein's resistance to statistical and probabilistic thinking extended beyond quantum mechanics to other areas. He reluctantly accepted that thermodynamics involves probabilities, but hoped this reflected our ignorance rather than nature's fundamental character. He resisted acknowledging that randomness might be ineliminable from physics. This resistance proved wrong, as quantum mechanics, statistical mechanics, and chaos theory all demonstrated irreducible unpredictability in different domains. His determinism also led him to underestimate consciousness's importance and the hard problem of explaining subjective experience. Einstein treated consciousness as epiphenomenal, a byproduct of physical processes with no causal efficacy. He showed little interest in philosophy of mind or psychology beyond basic behaviorist ideas. Contemporary debates about consciousness, qualia, and whether physical description can fully explain subjective experience did not engage him seriously. This represents a genuine limitation in Einstein's philosophy. Consciousness is among reality's most undeniable features, yet Einstein's physicalist worldview had difficulty accommodating it. Whether this reflects his error or consciousness, studies immaturity remains debated, but Einstein clearly had no solution to offer. Einstein's social vision, while admirable in its idealism, sometimes underestimated cultural diversity's value. His universalist emphasis on common humanity and reason sometimes suggested that cultural differences are superficial and should be transcended. Contemporary multiculturalism recognizes that diverse cultural traditions embody different valuable insights about human flourishing that should be preserved and respected, not dissolved into bland universalism. Einstein might respond that respecting cultural diversity is compatible with recognizing universal human values like dignity, freedom, and welfare that transcend culture. The challenge is balancing multicultural respect with ethical universalism, avoiding both cultural imperialism and moral relativism. Einstein's framework provides resources for this balance, but he did not develop them fully. His faith in science as morally and politically liberating has proven partially mistaken. Science has enabled tremendous human progress, but also environmental destruction, weapons of mass destruction, and techniques of surveillance and control. Scientific thinking does not automatically produce moral wisdom or prevent horrific applications of scientific knowledge. Einstein recognized this late in life regarding nuclear weapons, but his general optimism about science's role in human progress required more qualifications than he provided. Finally, Einstein's cosmic religion, while intellectually sophisticated, may not provide adequate resources for confronting suffering, loss, and injustice. Traditional religion offers comfort through promises of transcendence, meaning in suffering, and ultimate justice. Einstein's Spinozistic God offers only the cold comfort of understanding that everything follows necessarily from natural law. For most people facing tragedy, this provides little consolation. Einstein would likely respond that false comfort is worse than harsh truth. Better to face reality courageously than hide behind comforting illusions. But this response assumes that traditional religious belief is false, which Einstein cannot prove, and that his own interpretation of reality is correct, which quantum mechanics challenges. At minimum, his cosmic religion works better for understanding the universe than for navigating human suffering. These failures and limitations do not diminish Einstein's extraordinary achievements. Every thinker, no matter how brilliant, is constrained by their historical moment, personal temperament, and cognitive limitations. Einstein's mistakes reveal the human face behind the legendary figure, someone who struggled, erred, and persisted despite repeated failure. His willingness to be wrong in pursuit of truth exemplifies the scientific spirit, perhaps more than his successes. Part 10. Legacy and Living Debates. How scholars continue fighting over his ideas. Einstein's intellectual legacy remains vigorously contested across multiple disciplines. Physicists, philosophers, historians, and social theorists continue debating what his ideas mean, whether they were correct, and how they should influence contemporary thought. These debates are not merely academic, but shape research programs, educational approaches, and public understanding of science. Einstein, the historical figure, has transformed into Einstein, the contested symbol whose meaning different communities claim for competing purposes. In physics, the primary debate concerns whether Einstein's realist determinist approach to quantum mechanics might ultimately be vindicated. Most physicists accept the Copenhagen or instrumentalist interpretation. Quantum mechanics is a tool for predicting measurement outcomes, and questions about underlying reality are meaningless or unanswerable. A minority pursues Einstein's program of finding more complete theories that restore classical intuitions about reality. This minority has grown recently due to developments suggesting quantum mechanics might not be the final word. The measurement problem remains unsolved, and combining quantum mechanics with gravity requires modifications we do not yet understand. Some physicists argue that quantum mechanics is an effective theory, highly accurate within its domain, but not fundamental, similar to how thermodynamics is accurate but not fundamental. These neo-Einsteinian researchers pursue theories like objective collapse models, which add genuinely random collapses to quantum mechanics, or pilot wave theories that restore determinism at the cost of non-locality. They argue that Einstein was right to seek theories describing reality independently of observers, even if his specific proposals failed. Critics respond that nearly a century of experimental success makes quantum mechanics extraordinarily well established. Seeking to replace it with classical alternatives reflects metaphysical prejudice rather than scientific evidence. Better to accept quantum weirdness as genuinely how nature is than perpetually seeking failed classical alternatives. This debate will likely only be resolved, if at all, when quantum gravity is finally developed. If quantum gravity restores classical spacetime at the deepest level. With quantum mechanics emerging from underlying deterministic structures, Einstein's intuitions will be partially vindicated. If quantum mechanics remains fundamental with spacetime emerging from quantum processes, the Copenhagen view wins. Current evidence does not decisively favour either position. The philosophical debate about scientific realism continues using Einstein as a central figure. Scientific realists argue that successful theories approximately truly describe unobservable reality, so electrons, space-time curvature, and quantum fields really exist. Anti-realists argue that theories are tools for organizing experience and making predictions, with truth about unobservables either impossible or scientifically irrelevant. Einstein is claimed by both sides. Realists cite his insistence that physics should describe objective reality independent of observers. Anti-realists note his operational approach to simultaneity in special relativity, defining concepts through measurement procedures rather than independent existence. This ambiguity in Einstein's actual position allows both sides to invoke his authority. Contemporary philosophers like Bas van Fraassen defend anti-realism using arguments Einstein would have rejected, but which draw on his operational definitions. Others like Richard Boyd defend realism using Einstein's later arguments about quantum mechanics requiring realistic interpretation. The debate shows how Einstein's work raised fundamental questions that remain unresolved. In Philosophy of Time, Einstein's block universe interpretation of relativity continues generating controversy. Presentists argue that relativity does not actually require eternalism, because simultaneity's relativity only shows that the present is observer-dependent, not that past and future are equally real. They propose various ways of maintaining that only the present exists while accommodating relativity's insights. Eternalists respond that these attempts all smuggle in absolute simultaneity through hidden assumptions. Relativity really does require abandoning the common-sense view that the present is uniquely real. This debate connects to physics through quantum gravity proposals that treat time as emergent. If time is not fundamental, then both presentism and eternalism might be mistaken, reflecting our limited perspective rather than ultimate reality. The arrow of time problem Einstein's relativity raised remains unsolved. Why does time have an arrow, a distinction between past and future, if fundamental physics is time-symmetric? Proposals range from cosmological boundary conditions at the Big Bang to consciousness creating temporal asymmetry to time reversal symmetry being more approximate than previously thought. None has achieved consensus. Einstein's epistemology continues influencing philosophy of science debates about theory choice. How should scientists choose between empirically equivalent theories that make identical predictions, but differ in their ontological commitments or conceptual frameworks? Einstein emphasized theoretical virtues like simplicity, unification, and explanatory depth. Critics argue these values are subjective aesthetic preferences that do not reliably track truth. This debate affects contemporary physics disputes about string theory and quantum gravity approaches. String theorists argue their theory's mathematical elegance and unifying power make it likely true despite lacking experimental evidence. Critics respond that elegance has led physics astray before, and empirical testing is indispensable. Both sides invoke Einstein. String theorists point to his successful use of theoretical virtues in developing relativity, while critics note his failed unified field theory attempts. In cosmology, Einstein's influence appears in debates about the universe's nature and origin. His relativity provides the framework for modern cosmology, including Big Bang theory, cosmic expansion, and black holes. Yet his philosophical commitments to cosmic rationality and comprehensibility face challenges from findings suggesting the universe might be more contingent and arbitrary than Einstein assumed. The cosmological multiverse hypothesis proposes countless universes with different physical laws, explaining our life-permitting universe as selection bias. We necessarily observe a universe compatible with our existence. This hypothesis troubles many physicists because it abandons Einstein's expectation that fundamental physics should explain why laws are what they are, rather than different. If our laws result from random variation across universes, then physics cannot explain them, only describe them. Einstein would likely have rejected the multiverse as giving up on scientific explanation too easily. But defenders argue that sometimes we must accept uncomfortable implications of successful theories rather than clinging to philosophical preferences. This repeats the quantum mechanics debate. Does physics require philosophical satisfactoriness or only empirical accuracy? Einstein's political philosophy influences contemporary debates about democracy, socialism, and global governance. Progressive movements invoke his democratic socialism and warnings about capitalism's dangers. Critics point out that Einstein provided no realistic institutional proposals and that attempted socialist implementations produced tyranny. Debates about whether democratic socialism is possible or whether it inevitably degenerates into authoritarianism continue using Einstein as a reference point. His advocacy for world government influences contemporary globalism and cosmopolitanism. Proposals for strengthening international institutions, addressing climate change through global cooperation, and constraining nationalism draw inspiration from Einstein's vision. Critics argue that world government threatens freedom, and that national sovereignty, despite its dangers, provides important protection against tyranny. Einstein's framework shapes this debate without resolving it. In discussions of science's social role, Einstein exemplifies the engaged intellectual using scientific authority to promote progressive values. Some scholars celebrate this model, arguing scientists should actively address social problems. Others warn that Einstein's example shows the dangers. His political judgments often exceeded his expertise, and his celebrity gave undue weight to views that were sometimes naive. The contemporary resonance appears in debates about scientists advocating climate policy, artificial intelligence regulation, or biotechnology governance. Should scientists stick to providing information or actively campaign for particular policies? Einstein's example is cited by both sides, as a model of responsible public engagement or as a cautionary tale about overreach. Einstein's determinism influences contemporary neuroscience and criminal justice debates. As brain science reveals the neural basis of behavior, questions about free will and moral responsibility that Einstein grappled with become practically urgent. His compatibilist position, maintaining moral responsibility despite determinism by focusing on consequentialist justifications, shapes reform proposals emphasizing rehabilitation over retribution. Critics argue that eliminating retributive punishment based on determinist arguments risks undermining moral order and failing to express appropriate condemnation of serious wrongdoing. Defenders respond that Einstein-style consequentialism provides adequate justification for accountability while encouraging more humane approaches to criminal behavior. In education, Einstein's emphasis on creativity, intuition, and independent thinking influences pedagogical approaches. Many educational reformers invoke Einstein in arguing against rote learning and standardized testing, advocating instead for encouraging questioning imagination and conceptual understanding. Critics respond that Einstein's genius was exceptional and that most students benefit from more structured traditional instruction. This debate often involves mythologized versions of Einstein rather than careful attention to his actual views. He did criticize authoritarian education, but also valued rigorous training in fundamentals. He thought both creative imagination and disciplined mathematical reasoning were essential, not opposites. But popular invocations of Einstein in education debates rarely capture this nuance. Einstein's relationship with religion continues generating controversy. Atheists claim him as rejecting superstition and embracing scientific rationalism. Religious believers highlight his use of God language and cosmic religious feeling as showing compatibility between science and spirituality. Both interpretations have some textual support, but both oversimplify his subtle position. The contemporary debate about science and religion's relationship often uses Einstein as ammunition without carefully examining his actual views. New atheists, like Richard Dawkins, cite Einstein's rejection of personal God. Accommodationists, like Francis Collins, note Einstein's religious language and awe before nature. Neither camp fully engages his Spinozistic pantheism, which does not fit easily into science versus religion frameworks. In popular culture, Einstein has become a symbol whose meaning varies by context. He represents genius, obviously, but also eccentricity, social conscience, Jewish identity, German-American immigration success, scientific creativity, and absent-minded professor stereotypes. This symbolic Einstein often bears little relation to the historical figure, creating a mythology that shapes public understanding of science and scientists. Scholars debate whether this mythologization helps or harms public science understanding. It provides an accessible face for abstract science, making physics more relatable. But it also promotes misleading hero worship and misunderstanding of how science actually works, emphasizing individual genius over collaborative effort. The question of Einstein's contemporary relevance divides scholars. Some argue his ideas remain at science's cutting edge. Quantum mechanics, interpretation, unified theory approaches, cosmological questions all continue trajectories Einstein began. His philosophical framework about realism, rationality and comprehensibility still guides much theoretical physics. Others contend that Einstein's paradigm has been superseded. Quantum mechanics shows that classical realism fails. Contemporary physics is comfortable with mathematical formalism without insisting on intuitive physical pictures. String theory and other approaches embrace abstractions that Einstein would have rejected. His influence reflects historical importance rather than ongoing relevance to cutting-edge research. The truth likely lies between these extremes. Einstein's specific theories remain foundational. Special and general relativity are cornerstones of modern physics, tested repeatedly and relied on constantly. His broader philosophical approach, emphasizing unification, elegance and rationality, continues influencing some researchers, while others pursue more empiricist or instrumentalist programs. Perhaps Einstein's deepest legacy is not any particular theory, but the demonstration that physics can be revolutionary. Before Einstein, physics seemed nearly complete, requiring only minor refinements. He showed that apparently obvious concepts like absolute time and flat space could be wrong, that mathematical reasoning could overturn centuries of scientific consensus, that unification of disparate phenomena was possible. This revolutionary potential that Einstein revealed continues inspiring physicists to question fundamentals and seek radical alternatives. Yet his failures also teach important lessons. Revolutionary thinking sometimes produces breakthroughs and sometimes leads to decades wasted on impossible programs. Trusting theoretical beauty and mathematical elegance works brilliantly until it does not. Philosophical commitments can both enable revolutionary insight and create blind spots, preventing recognition of genuine discoveries that violate preferred principles. The ongoing scholarly debates about Einstein reflect deeper uncertainty about science's nature and aims. Is physics fundamentally about describing reality or producing accurate predictions? Should theories be judged primarily by empirical success, or do theoretical virtues matter independently? Can humans ever achieve complete understanding of nature, or must we accept fundamental limits to comprehension? Einstein took strong positions on all these questions, and his successes and failures provide evidence for multiple sides. His relativity shows that theoretical reasoning can achieve deep truth about reality. His quantum mechanics rejection shows that philosophical preference can blind us to empirical discoveries. His unified field theory suggests that mathematical beauty alone is insufficient. His lasting influence shows that asking fundamental questions matters even when answers remain elusive. Future developments will continue reshaping Einstein's legacy. If quantum gravity restores classical space-time as emergent from deeper structures, Einstein's realist program gains support. If quantum mechanics remains fundamental with no underlying determinism, Copenhagen interpretation's descendants win. If unified theory is eventually achieved, Einstein's faith in nature's unity is vindicated even if his specific attempts failed. If physics remains perpetually disunified across domains, Cartwright's patchwork view prevails. What remains certain is that Einstein transformed how humans understand reality and our place within it. His ideas force confronting profound questions about time, causality, determinism, knowledge, and human agency that cannot be avoided. Scholars will continue fighting over his legacy because the issues he raised cut to the heart of what it means to understand the universe and ourselves. Einstein's deepest contribution may be not answers, which remain contested, but questions that reveal how much we still do not comprehend despite our progress. In the end, Einstein embodied the scientific spirit. Insatiable curiosity, intellectual courage, willingness to challenge authority, and commitment to truth regardless of personal cost. His confidence that the universe is comprehensible, that human reason can grasp nature's deepest patterns, that understanding is worth pursuing for its own sake, continues inspiring scientists and philosophers today. Whether this confidence is ultimately justified remains unknown, but the attempt to answer Einstein's questions, to understand what he understood and to see further still, drives science forward into unknown territories where new revolutions may await.